Imagine looking up at the night sky and seeing something that shouldn't be there, a single object appearing twice, or even multiple times, as if the universe itself were playing tricks on your eyes. But this isn't an illusion. It's a real effect caused by the warping of space-time itself. This is what happens with lensed quasar echoes, one of the strangest and most mind-bending phenomena in astrophysics. And what's even crazier? These echoes don't just bend light. They bend time itself. But how is that possible? How can we see the same event happening at different times in different places? And what does that tell us about the universe? That's what we're about to uncover. And trust me, once you understand how this works, you'll never look at the night sky the same way again. Lensed quasar echoes are one of those rare cosmic events that force us to rethink everything we know about space, time, and even reality itself. To understand them, we need to start with quasars, some of the brightest, most powerful objects in the universe. Quasars are essentially supermassive black holes at the centers of distant galaxies, surrounded by disks of incredibly hot, glowing material. These disks shine so brightly that they can outshine entire galaxies, making quasars some of the most distant objects we can see. But something weird happens when the light from a quasar travels toward us and encounters a massive object along the way, like a galaxy or a cluster of galaxies. According to Einstein's theory of general relativity, gravity isn't just a force pulling objects together, it actually bends the fabric of space-time. And when light passes through this warped space-time, it follows curved paths, just like how a river bends around obstacles. This effect, called gravitational lensing, can create multiple images of the same distant object. That's why we sometimes see a quasar appear in different places in the sky. But here's where it gets even stranger. Light doesn't always take just one path through the warped space-time. Some rays of light take a shorter route, arriving at Earth first. Others take a longer, more curved route, arriving later. The result? We see the same event happening more than once, like watching a movie that plays at different times on different screens. This is what we call a lensed quasar echo. And this isn't just some abstract theory. We've actually seen it happen. Astronomers have observed quasars flickering, with the same flicker appearing in multiple images, but at different times. This means that, in a way, gravitational lensing lets us look into the past. By comparing these echoes, scientists can measure the delay between them and use that information to study the universe in ways we never could before. But here's the mind-blowing part. These time delays aren't just random. They can tell us something deep about the nature of dark matter, dark energy, and even the expansion rate of the universe itself. In fact, lensed quasar echoes are helping scientists solve one of the biggest mysteries in physics: the true value of the Hubble constant, the number that describes how fast the universe is expanding. Different methods of measuring it have given different results, leading to what scientists call the Hubble tension. Lensed quasar echoes might just be the key to resolving this cosmic mystery once and for all. And we're only scratching the surface. The more we study these echoes, the more we realize how much they can teach us, not just about quasars, but about the very structure of space-time itself. Could they help us test theories about alternate dimensions? Could they reveal hidden properties of black holes? Could they even give us hints about the true nature of time? The deeper we go, the more questions emerge. And that's why lensed quasar echoes are one of the most fascinating and mysterious phenomena in the universe. They challenge our understanding of reality and force us to confront the strangest aspects of physics. But to fully grasp their significance, we need to go deeper. We need to break down exactly how they work, what they reveal, and why they might be the key to answering some of the biggest questions in science. So let's go all the way down the rabbit hole. Lensed quasar echoes don't just reveal themselves randomly. They are rare, requiring a precise cosmic alignment. For a quasar's light to be bent and split into multiple images, there needs to be a massive object directly between the quasar and us. This intervening object, often a massive galaxy or a cluster of galaxies, acts as a gravitational lens, warping spacetime in just the right way to create multiple copies of the quasar's image. But here's where things get really interesting. These multiple images aren't just visual duplicates. They are time-shifted versions of the same event. Think about it like this. Imagine you're watching a lightning storm from a distance. If the storm is far away, you'll see the lightning before you hear the thunder. That's because light travels much faster than sound. But now, imagine the storm's lightning flashes are split into different paths, one traveling directly to you, another bouncing off a mountain before reaching you. You'd see the same flash twice, but at different times. That's exactly what's happening with lensed quasar echoes. The light from a quasar takes different paths through the warped spacetime around a massive object, and since some paths are longer than others, the images we see arrive at different times. This means that if a quasar suddenly flares up, if it experiences a sudden brightening event, for example, we might see that same flare appear in one image first, and then again in another image weeks, months, or even years later, depending on the difference in light travel time. In essence, we're watching a cosmic event replay itself in real time, but through the lens of gravity itself. Now, why does this matter? Because these time delays aren't just cool to observe, they hold the key to unlocking some of the deepest mysteries in astrophysics. Scientists can measure these delays very precisely, down to a fraction of a day. And by analyzing them, they can learn things like the exact distribution of matter in the lensing galaxy, how much dark matter it contains, and even whether there are hidden clumps of invisible mass that we wouldn't be able to detect otherwise. In other words, lensed quasar echoes give us a way to map out the invisible structure of the universe. But there's something even bigger at stake here, something that could change our understanding of the cosmos itself. One of the biggest debates in modern physics is about the expansion of the universe. We know that space is stretching over time, causing galaxies to move away from each other. The speed of this expansion is described by the Hubble constant, a number that scientists have been trying to pin down for decades. The problem? Different methods of measuring the Hubble constant have given different answers, leading to a crisis in cosmology known as the Hubble tension. This is where lensed quasar echoes come in. By measuring the time delays between different images of a quasar and applying mathematical models, scientists can use these echoes as a cosmic stopwatch, measuring how fast the universe is expanding. Unlike other methods, which rely on indirect assumptions, gravitationally lensed quasars provide a direct way to test the expansion rate. And the results so far? They seem to support one of the conflicting measurements, deepening the mystery rather than solving it. So what does this mean? It means that either there's something wrong with our current understanding of the universe, or there's some unknown physics at play that we haven't yet discovered. Some scientists even speculate that lensed quasar echoes could provide evidence for exotic new physics, things like variations in the fundamental constants of nature, or even hints of unknown forces shaping the cosmos. And there's still more. These echoes aren't just a tool for cosmology. They're also a window into the wild, chaotic behavior of quasars themselves. Quasars are powered by supermassive black holes that are constantly feeding on surrounding matter, pulling in gas and dust at incredible speeds. This feeding process isn't smooth, it's turbulent, with sudden bursts of energy and unpredictable fluctuations. When we observe these fluctuations in lensed quasars, we get a rare chance to study the feeding habits of black holes in extreme detail. Imagine trying to study an explosion, but instead of just seeing it once, you get to see it multiple times from different angles, at different moments in time. That's essentially what lensed quasar echoes allow us to do. They let us watch a black hole devour its surroundings in slow motion, revealing the intricate processes at work in one of the most violent environments in the universe. And if that wasn't enough, there's yet another layer to this. Some researchers believe that lensed quasar echoes could even help us detect the presence of primordial black holes, tiny black holes that may have formed in the earliest moments of the universe. These objects, if they exist, could be a major component of dark matter, the invisible substance that makes up most of the universe's mass. If a primordial black hole happens to sit along our line of sight to a lensed quasar, it could slightly alter the time delays, leaving behind a detectable signature. In other words, by studying these echoes, we might be able to find evidence of the hidden building blocks of the cosmos itself. But the implications don't stop there. The very concept of lensed quasar echoes challenges our fundamental understanding of time. If light from a single event can reach us at multiple moments, Does that mean time is truly linear? Could there be deeper, hidden layers to time that we haven't yet grasped? Some physicists have even speculated that effects like these could one day help test theories about the nature of time itself, whether it flows in one direction or whether it's part of a larger, more complex structure. And all of this, the cosmic mysteries, the insights into black holes, the hidden structure of the universe, is packed into these rare, fleeting moments where light bends around a galaxy and reveals an echo from the past. But we're still just scratching the surface. Scientists are only beginning to explore the full potential of lensed quasar echoes, and with new telescopes like the James Webb Space Telescope and upcoming observatories like the Vera Rubin Observatory, we're likely to discover even more of them in the coming years. Each new discovery could bring us one step closer to answering some of the biggest questions in physics. And that's why this topic is so fascinating. Lensed quasar echoes are more than just a strange trick of gravity. They are one of the most powerful tools we have for exploring the universe. They allow us to measure cosmic expansion, map invisible matter, study black holes in detail, and even question the nature of time itself. And as our technology improves, who knows what else they might reveal? The universe has a way of surprising us, and sometimes, the answers we're looking for aren't in the distant future, they're already out there, encoded in the echoes of light that have been traveling for billions of years, waiting for us to decipher them. The deeper we dive into the study of lensed quasar echoes, the more we realize how much information is hidden in these delayed flashes of light. Every time we discover a new case of a quasar being gravitationally lensed, we unlock another piece of the puzzle. Scientists have developed advanced techniques to analyze these echoes, breaking down the data into precise time delays, brightness fluctuations, and spectral shifts. These observations allow us to test theories of relativity, probe the distribution of dark matter, and even refine our understanding of how black holes grow over cosmic time. One of the most important aspects of lensed quasar echoes is the way they allow us to directly test Einstein's theory of general relativity on cosmic scales. General relativity predicts exactly how light should bend around a massive object, and by studying lensed quasars, scientists can compare real observations to theoretical predictions. So far, the theory has held up incredibly well. But the more precise our measurements become, the greater the chance that we might find small discrepancies, tiny deviations that could hint at new physics beyond Einstein's equations. This is why astronomers are pushing the limits of their observational techniques. By using high-resolution space telescopes like Hubble and JWST, as well as powerful ground-based telescopes equipped with adaptive optics, scientists are able to measure the positions and brightness variations of lensed quasars with unprecedented accuracy. Some of these quasars have time delays of just a few days, while others span several years. Each one provides a different perspective on the complex interplay between gravity, time, and light. But here's something even more intriguing. Lensed quasar echoes aren't just useful for studying quasars themselves. They also allow us to investigate the properties of the lensing galaxies. Normally, a galaxy billions of light years away would be nothing more than a faint smudge in the sky, too distant for us to study in detail. But when that galaxy acts as a gravitational lens, it amplifies and distorts the light of the background quasar, effectively turning it into a natural magnifying glass. By analyzing how the quasar's light is bent, astronomers can reconstruct the distribution of matter within the lensing galaxy, revealing details about its dark matter content, stellar populations, and even hidden substructures. This is particularly important when it comes to testing our models of dark matter. Dark matter is an invisible substance that makes up about 85% of the universe's total mass, yet we have never directly observed it. Scientists believe it forms a vast cosmic web, providing the scaffolding upon which galaxies and galaxy clusters form. But the exact nature of dark matter is still a mystery. One way to probe its properties is by looking at how lensed quasar echoes behave. If dark matter is smoothly distributed, then the time delays between quasar echoes should follow a predictable pattern. But if dark matter is clumpy or consists of small, unseen structures, then these time delays could be slightly different from what we expect. And guess what? Some recent studies have hinted at exactly that. There have been cases where lensed quasars showed unexpected variations in their time delays, suggesting that there may be tiny clumps of dark matter, possibly primordial black holes or exotic dark matter particles, scattered throughout the lensing galaxy. If this turns out to be true, it could change our entire understanding of how dark matter is distributed and what it's made of. But it gets even weirder. Some scientists have speculated that lensed quasar echoes could provide indirect evidence for so-called fuzzy dark matter, a hypothetical form of dark matter made up of ultralight particles that behave more like waves than particles. If these waves interfere with each other, they could create subtle ripples in space-time, affecting the time delays in ways that might be detectable with extremely precise measurements. This would be a groundbreaking discovery, providing a completely new way to test theories about the fundamental nature of the universe. And speaking of fundamental nature, there's yet another mind-bending implication of lensed quasar echoes, one that touches on the nature of time itself. We tend to think of time as a linear sequence, moving forward at a constant rate. But lensed quasar echoes challenge that view. When we observe multiple images of the same event arriving at different times, it raises deep questions about whether time is truly as fixed as we perceive it. Some physicists have even suggested that effects like these could be used to test ideas about the nature of time in the context of quantum mechanics and relativity. Could time be more fluid than we think? Could there be hidden dimensions affecting how light propagates through the universe? While these are still open questions, the mere fact that lensed quasar echoes exist suggests that time is more complex than our everyday experience leads us to believe. And then there's the possibility of using lensed quasars to detect exotic cosmic phenomena. Some researchers have proposed that if a gravitational wave, one of those ripples in space-time caused by cataclysmic cosmic events, were to pass through a lens system, it could alter the time delays between quasar echoes. This would provide a completely new way to study gravitational waves, complementing detectors like LIGO and Virgo. Imagine being able to use distant quasars as natural gravitational wave detectors, allowing us to study the most violent events in the universe from an entirely new perspective. But perhaps one of the most exciting developments in this field is the upcoming generation of telescopes that will dramatically increase the number of known lensed quasars. The Vera C. Rubin Observatory, set to begin full operations soon, is expected to discover thousands of new gravitationally lensed quasars, providing an unprecedented amount of data for astronomers to work with. With this influx of observations, scientists will be able to refine their models, test new theories, and potentially uncover completely unexpected phenomena. And let's not forget the role of artificial intelligence in all of this. Modern astronomers are increasingly relying on AI and machine learning algorithms to analyze the vast amounts of data coming in from telescopes. These algorithms can automatically identify lensed quasar systems, measure their time delays, and even detect subtle anomalies that might be the key to new discoveries. In a way, AI is becoming an essential tool in our quest to understand the universe, helping scientists sift through the cosmic noise to find the hidden signals buried within. So, where does this leave us? We've gone from the simple observation of light bending around a massive object to the realization that these echoes can unlock some of the deepest mysteries in astrophysics. We've seen how lensed quasar echoes can help measure the expansion of the universe, probe the nature of dark matter, test Einstein's theories, and even challenge our understanding of time. And with new telescopes and AI-driven analysis, we're on the brink of discovering even more. But the truth is, we're just at the beginning of this journey. Every time we refine our measurements, every time we discover a new lensed quasar, we're peeling back another layer of the cosmic mystery. The universe is speaking to us through these echoes, flashes of light that have traveled billions of years, distorted by gravity, delayed by time, and waiting for us to decode their message. And as we continue to push the boundaries of what's possible, one thing is certain. The more we learn about lensed quasar echoes, the more we realize how much we still don't know. The universe is full of secrets, and sometimes, those secrets are hidden in the flickering light of a distant quasar, playing out across time, waiting to be understood. Lensed quasar echoes represent a cosmic phenomenon so intricate and profound that they challenge our very understanding of space, time, and gravity. We've seen how these light echoes, stretched across billions of years, serve as cosmic measuring tools, allowing us to probe the fundamental structure of the universe. But their true potential is still being uncovered. With each new discovery, we refine our theories, develop better observational techniques, and uncover more layers of cosmic complexity. One of the most groundbreaking aspects of lensed quasar echoes is their potential to test alternative models of gravity. While general relativity has been remarkably successful in explaining gravitational lensing, there are competing theories that propose modifications to Einstein's equations. Some of these alternative theories suggest that gravity might behave differently on cosmic scales, affecting how light bends and how time delays occur. By studying the precise timing of quasar echoes, astronomers can look for subtle deviations that might indicate the presence of new physics. For example, some theories propose that gravity might have a hidden, fifth force that only reveals itself under extreme conditions. Others suggest that dark energy, the mysterious force accelerating the expansion of the universe, could be a sign that our understanding of gravity is incomplete. Lensed quasar echoes provide one of the best ways to test these ideas, offering a natural laboratory where the interplay of light, mass, and space-time can be observed with unparalleled precision. But the implications go even deeper. Some scientists have speculated that the strange patterns observed in lensed quasar echoes could be linked to the nature of quantum gravity, a yet undiscovered theory that unifies quantum mechanics with general relativity. If space-time itself is not continuous but instead has a hidden, quantum-level structure, then the way light travels through the universe might be subtly altered. This could manifest in tiny, unexpected shifts in quasar time delays, shifts that, with the right observational tools, we might one day detect. This brings us to another fascinating possibility. Could lensed quasar echoes reveal evidence for cosmic strings? Cosmic strings are hypothetical one-dimensional defects in space-time, left over from the early universe. They are predicted by some theories of high-energy physics, including string theory, and they could act as additional gravitational lenses, distorting and delaying quasar light in unusual ways. If a cosmic string were to pass between us and a lensed quasar, it could create additional echoes, splitting the light into even more images or altering the time delays in ways that don't match traditional gravitational lensing models. Scientists are actively searching for these anomalies. With the increasing sensitivity of telescopes and advanced machine learning techniques, we are now able to detect faint, unexpected variations in lensed quasar systems. If even one of these anomalies turns out to be a sign of a cosmic string, it would be one of the biggest discoveries in the history of physics, evidence that space-time itself carries scars from the birth of the universe. But even as we consider these grand possibilities, there are more practical applications of lensed quasar echoes that could change the way we study the cosmos. One of these is the possibility of using them to map the cosmic web, the vast, filamentary structure of galaxies and dark matter that spans the universe. By carefully analyzing how quasar light is delayed and distorted, astronomers can create detailed maps of the mass distribution in the universe, revealing where dark matter is concentrated and how it interacts with normal matter over cosmic time. This technique could also help us understand the mysterious phenomenon known as cosmic voids, vast, empty regions of space that contain very few galaxies. These voids are some of the least understood structures in the universe, and their properties could hold clues about the nature of dark energy and the fundamental forces shaping the cosmos. If lensed quasar echoes can be used to study how light passes through these voids, we might gain unprecedented insight into the large-scale structure of the universe. Another exciting development is the use of lensed quasars as a kind of natural telescope to study distant galaxies. Because gravitational lensing magnifies the light of background objects, it allows us to see galaxies that would otherwise be too faint to observe. In some cases, lensed quasars provide such extreme magnification that we can study the detailed structure of galaxies at the edge of the observable universe, effectively looking billions of years into the past to witness the early stages of galaxy formation. This is especially important for understanding the evolution of supermassive black holes. We know that quasars are powered by these enormous black holes, but how did they grow so large in the first place? One of the biggest mysteries in astrophysics is how some black holes in the early universe became so massive in such a short amount of time. By studying lens quasars at extreme distances, we can gather clues about their feeding habits, their interactions with their host galaxies, and the conditions that allowed them to form so rapidly. And here's something even more mind-blowing. Lens quasar echoes could potentially be used to test the idea of a cyclic universe. Some cosmological models suggest that the universe goes through cycles of expansion and contraction, rather than having a single beginning with the Big Bang. If this is true, there might be subtle imprints of previous cycles embedded in the way light propagates across cosmic distances. Lens quasar echoes, with their precisely measurable time delays, could provide a unique way to search for these hidden signals, offering clues about the ultimate fate of the universe. The future of this field is incredibly promising. With next-generation observatories like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope set to launch in the coming years, we are on the verge of a massive explosion in the number of known lens quasars. These telescopes will scan huge portions of the sky, detecting new gravitational lensing events in real time and providing astronomers with an unprecedented dataset. Meanwhile, artificial intelligence is becoming an increasingly important tool in analyzing these observations. Machine learning algorithms can now automatically identify lens quasars, measure their time delays, and even predict when the next echoes will arrive. This means that instead of waiting passively for quasar echoes to appear, scientists can proactively schedule telescope observations to catch them at just the right moment. And then there's the possibility of using lens quasars in ways we haven't even thought of yet. Some researchers are exploring whether they could help test exotic theories of space-time, such as the idea that our universe is a hologram. Others are investigating whether gravitational lensing could be used to amplify signals from distant extraterrestrial civilizations, an idea that sounds straight out of science fiction but is being seriously considered by some astronomers. No matter what the future holds, one thing is clear: lensed quasar echoes are far more than just a curiosity. They are a key to unlocking some of the deepest mysteries of the cosmos, providing a window into the fundamental nature of space, time, and gravity. Every new discovery in this field brings us closer to answering some of the biggest questions in science, questions about the nature of reality itself. And as telescopes become more powerful, as AI continues to refine our observational techniques, and as new theories push the boundaries of what we think we know, the echoes of distant quasars will continue to whisper their secrets across the vastness of space and time. We are only beginning to listen. Lensed quasar echoes are not just a phenomenon of deep space. They are a cosmic conversation happening across billions of years. Every photon we receive from these distant quasars has traveled an unimaginable distance, bending around massive galaxies and clusters, splitting into multiple paths, and arriving at different times. This natural delay in light provides us with a unique window into the past, allowing us to study the universe as it was billions of years ago. But what if these echoes also hold secrets about the very nature of time itself? One of the most profound questions in physics is whether time is an absolute, continuous flow or if it is something more complex. The study of lensed quasar echoes has opened up discussions about whether time might be affected by the same distortions that affect space. Some theories suggest that gravity doesn't just bend light, it might also warp time itself in subtle ways that we have yet to detect. If this is true, then the time delays observed in lensed quasars might not just be due to the extra distance the light has to travel but could also hint at hidden distortions in the fabric of time itself. This connects to an even bigger question: could time flow differently in different parts of the universe? Some physicists have proposed that time might not be uniform everywhere, that in regions of extreme gravitational influence, time could slow down or speed up in ways that are not currently predicted by relativity. If these variations exist, they would have a measurable effect on lensed quasar echoes, causing tiny but detectable shifts in the expected time delays. Observing such an effect would be a groundbreaking discovery, challenging our entire understanding of how time operates on a cosmic scale. But lensed quasar echoes do more than challenge our theories of time. They also force us to confront the mysterious nature of dark matter. We know that dark matter makes up about 85% of the total matter in the universe, yet we have never observed it directly. We only know it exists because of its gravitational effects on visible matter and light. Lensed quasars provide one of the best tools for mapping dark matter, because the way light bends around a galaxy can tell us exactly how much mass is there, even the mass we can't see. By analyzing the precise structure of quasar echoes, astronomers can detect hidden clumps of dark matter that traditional methods might miss. These clumps could be small, isolated regions of dark matter, or they could be part of a larger web-like structure that connects galaxies across cosmic scales. If we can map these structures in detail, we might finally get closer to understanding what dark matter actually is, whether it's made of undiscovered particles, primordial black holes, or something even stranger. Some scientists are even considering the idea that lensed quasar echoes could provide hints about dark energy, the mysterious force that is accelerating the expansion of the universe. If dark energy is not a constant force but instead varies over time, then the way quasar echoes behave across different eras of cosmic history might reveal those variations. This could help solve one of the biggest puzzles in modern physics. Why is the universe expanding faster than expected? And what does that mean for its ultimate fate? As if that weren't enough, there is another mind-bending possibility. What if some of the anomalies observed in lensed quasar echoes are actually signs of exotic cosmic objects that have never been seen before? Some theorists have suggested that objects like primordial wormholes, tiny, ancient shortcuts through space-time, could exist in the universe. If a wormhole happened to be positioned in just the right place between us and a lensed quasar, it could create additional distortions in the light, potentially leading to unexplained time delays or unexpected changes in brightness. These ideas might sound speculative, but they are being taken seriously because lensed quasars provide such precise, measurable data. Unlike many other astrophysical phenomena, where observations are often uncertain or incomplete, lensed quasars offer a unique level of precision. The exact timing of light echoes can be predicted with incredible accuracy, and any deviations from those predictions could signal something truly new, something that challenges our understanding of the universe itself. Looking ahead, the future of lensed quasar research is incredibly exciting. With the upcoming generation of telescopes, including the Vera C. Rubin Observatory, the James Webb Space Telescope, and the European Space Agency's Euclid mission, we are about to witness an explosion of new data. These telescopes will be able to detect more lensed quasars than ever before, with even greater detail and accuracy. They will allow us to observe quasar echoes in real time, catching new lensing events as they happen and refining our models of the universe in ways that were once impossible. Artificial intelligence and machine learning are also playing an increasingly important role in this research. Advanced algorithms can now scan massive datasets to identify lensed quasars automatically, measure their time delays, and even predict when new echoes will appear. This automation allows astronomers to focus on analyzing the results and testing new theories, rather than spending years manually searching through images. But perhaps the most exciting possibility of all is that lensed quasar echoes might eventually provide evidence for something completely unexpected, something we haven't even thought of yet. Throughout history, some of the greatest discoveries in science have come from anomalies, observations that didn't match existing theories and forced us to rethink our understanding of the universe. If lensed quasar echoes contain such anomalies, they could lead to the next great breakthrough in physics. As we continue to refine our understanding of gravitational lensing, time delays, and cosmic structures, we are pushing the boundaries of what we know about space, time, and reality itself. Lensed quasar echoes are more than just a tool for measuring the universe. They are a cosmic puzzle, a mystery waiting to be solved. And with every new observation, every new dataset, and every new theory, we are one step closer to uncovering the hidden truths of the cosmos. But the echoes of quasars are not just about the distant past. They are a message from the universe, sent across billions of years, waiting for us to decode them. What they reveal could change everything we think we know, not just about space, but about the very nature of existence. Lensed quasar echoes challenge us to rethink the nature of light, gravity, and time itself. These echoes, delayed signals from some of the most powerful objects in the universe, carry information that could unravel some of the deepest mysteries in astrophysics. But what if they also reveal something more? Something that not only changes our understanding of the cosmos but forces us to reconsider the very way we perceive reality? One of the most profound implications of studying lensed quasars is how they push the limits of Einstein's theory of general relativity. For over a century, general relativity has been the foundation of our understanding of gravity, predicting how massive objects bend light and distort space-time. But there are still gaps, mysteries that remain unsolved. If lensed quasar echoes show even the slightest deviation from what Einstein's equations predict, it could mean that general relativity is incomplete. Scientists have already noticed a few puzzling inconsistencies. Some quasar echoes take longer to arrive than they should, even after accounting for all known factors like the mass of the lensing galaxy and the curvature of spacetime. Could this mean that our model of gravity needs modification? Some physicists believe these anomalies might hint at an undiscovered aspect of gravity, one that only becomes noticeable at cosmic scales. One possible explanation comes from modified gravity theories, which propose that gravity behaves differently at extremely large distances than it does near planets and stars. If these theories are correct, they could explain why galaxies rotate faster than expected without requiring dark matter. Lensed quasar echoes provide a direct way to test such theories, because even small changes in the way gravity works would affect the precise timing of light echoes. But what if the anomalies aren't due to modified gravity at all? What if they are instead evidence of something even stranger, hidden structures in spacetime itself? Some physicists have proposed that the universe might contain structures called cosmic strings, thin, ultra-dense filaments of energy left over from the early universe. These strings, if they exist, could subtly affect how light travels, creating additional distortions in lensed quasar echoes. Cosmic strings are hypothetical, but if they exist, they would be relics from the first moments of the universe's existence, fossils from a time when the fundamental forces of nature were still taking shape. If lensed quasar echoes reveal unexpected patterns in light delays, they could be the first real evidence that these exotic structures are out there, stretching across the cosmos. Another possibility is that lensed quasar echoes might hold clues about the mysterious phenomenon known as vacuum energy. In quantum physics, empty space is not truly empty, it is filled with fluctuating energy, which scientists call the quantum vacuum. Some researchers believe that variations in this vacuum energy could affect how light propagates through space. If this is true, then measuring tiny shifts in quasar echoes could provide insight into the nature of quantum spacetime, one of the biggest unsolved problems in modern physics. Even more mind-bending is the idea that quasar echoes could provide indirect evidence for the multiverse. Some cosmologists believe that our universe is just one of many, each with its own set of physical laws. If there are tiny leaks or interactions between universes, they might subtly affect the way light travels over billions of years. These effects could show up in the data from lensed quasars, revealing themselves as unexplained delays or unexpected fluctuations in brightness. Of course, all of these ideas, modified gravity, cosmic strings, quantum vacuum effects, and the multiverse, are highly speculative. But the beauty of lensed quasar echoes is that they give us real, measurable data that can be tested against these theories. Unlike many aspects of theoretical physics, which are difficult or even impossible to test directly, quasar echoes provide a natural cosmic laboratory. By analyzing these echoes with extreme precision, we might be able to rule out some theories and find hints that point toward entirely new physics. This is why upcoming telescope projects are so important. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will revolutionize our ability to detect lensed quasars. Over the course of a decade, LSST will scan the entire sky, capturing millions of galaxies and identifying thousands of new lensed quasars. With this massive dataset, astronomers will be able to measure time delays with unprecedented accuracy, detecting even the smallest anomalies. Meanwhile, the James Webb Space Telescope, JWST, will allow us to study lensed quasars in incredible detail, capturing infrared light that has been stretched by the expansion of the universe. This will help us analyze the environments around quasars, revealing how their light interacts with intergalactic gas, dust, and possibly even exotic structures. One of the most exciting possibilities is that these telescopes might discover new types of gravitational lenses, ones that involve not just galaxies, but entire galaxy clusters or even cosmic voids. These extreme lensing events could amplify the echoes of quasars in unexpected ways, revealing even more about the large-scale structure of the universe. But what about artificial intelligence? Machine learning is already transforming the study of lensed quasars. Traditional methods of identifying and analyzing gravitational lenses require painstaking manual work, but AI can skim through massive datasets in seconds, automatically detecting lensing events and measuring time delays. These algorithms are becoming so advanced that they can even predict when new quasar echoes might appear in the future, allowing astronomers to prepare their observations in advance. And then there's the question of dark energy, the force responsible for the accelerating expansion of the universe. If dark energy is not a constant but changes over time, then quasar echoes could provide one of the best ways to detect these changes. By comparing echoes from quasars at different distances, effectively looking back in time, we might see subtle shifts that reveal how dark energy has evolved over billions of years. If we could determine whether dark energy is increasing, decreasing, or fluctuating, it would completely reshape our understanding of the universe's fate. Right now, we don't know whether the universe will expand forever, slow down, or even collapse in on itself. Quasar echoes might provide the missing piece of the puzzle. Beyond dark energy, there's another mystery that quasar echoes could help solve: the nature of supermassive black holes. Every large galaxy has a supermassive black hole at its center, and quasars are powered by these immense objects consuming matter at an incredible rate. But how did these black holes get so big so quickly? Some quasars formed less than 1 billion years after the Big Bang, yet they already contain billions of times the mass of the Sun. One idea is that the first black holes were much larger than expected, formed not from collapsing stars, but directly from vast clouds of gas in the early universe. If this is true, then analyzing the echoes of the most ancient quasars could provide evidence for these so-called direct collapse black holes. Every time we study lensed quasar echoes, we are peering into the most distant past, unraveling the secrets of the cosmos one photon at a time. These echoes are like messages from the universe's infancy, traveling for billions of years only to reach us now. And with every new observation, we are rewriting the history of space, time, and everything in between. Lensed quasar echoes are not just relics of the past. They are active beacons that allow us to probe the nature of time itself. When light from a quasar is split and delayed by a massive object, it creates a kind of natural time machine. The multiple paths that the light takes mean that some photons arrive at Earth later than others, even though they originated from the same event billions of years ago. This effect allows astronomers to see different moments of a quasar's activity at different times, effectively watching its past and present simultaneously. But what if this phenomenon could tell us something even deeper about the nature of time? One of the most controversial ideas in modern physics is that time might not be a fundamental property of the universe but rather an emergent one, something that arises from deeper physical principles. If this is true, then quasar echoes might provide a way to test whether time behaves differently under extreme conditions. For example, some physicists propose that at the smallest scales, time might not be continuous but instead behave in discrete jumps, much like pixels on a screen. If quasar echoes reveal inconsistencies in the timing of light arrival, it could hint at the quantum nature of time itself. But the mysteries don't stop there. The fact that lensed quasar echoes allow us to measure time so precisely means they could also help us test one of the biggest paradoxes in cosmology: the Hubble tension. This is the ongoing disagreement between different methods of measuring the expansion rate of the universe. Observations of the cosmic microwave background suggest one value for the Hubble constant, while measurements based on nearby supernovae suggest a different value. Lensed quasars provide a completely independent way to measure cosmic expansion by using time delays between multiple images. If this method confirms one value over the other, it could help resolve one of the most debated mysteries in modern physics. Even more intriguing is the possibility that quasar echoes could reveal variations in fundamental constants of nature. The speed of light, the strength of gravity, and other physical constants are assumed to be the same everywhere in the universe. but some theories suggest they might change over vast cosmic distances. If quasar echoes show unexpected shifts in their timing, it could be a sign that these fundamental constants are not as fixed as we thought. This idea ties into one of the most speculative but fascinating concepts in physics: the existence of extra dimensions. Some theories, particularly those related to string theory, suggest that our universe might have more than the three spatial dimensions we experience. If true, these extra dimensions could subtly affect how light travels, creating small but detectable differences in the arrival times of quasar echoes. By studying these variations, scientists might find indirect evidence for hidden dimensions lurking beyond our perception. And what about dark matter? One of the biggest questions in astrophysics is the true nature of the invisible substance that makes up most of the universe's mass. Some scientists believe dark matter could be made up of exotic particles that interact with light in unexpected ways. If quasar echoes show small fluctuations that cannot be explained by known physics, it could be a sign that dark matter is affecting the way light travels through space. Even more bizarre is the idea that lensed quasar echoes might help us detect so-called dark photons. These hypothetical particles are proposed as a way to explain why dark matter doesn't interact with normal matter in the same way that regular particles do. If dark photons exist, they might create small distortions in the way light propagates, and quasar echoes could be the key to spotting them. Another possibility is that lensed quasars might be able to test the idea of a cyclic universe, the concept that the cosmos goes through endless cycles of expansion and contraction. If this model is correct, then subtle imprints from previous cycles might be hidden in the structure of space-time itself. Quasar echoes could help reveal these imprints, giving us clues about whether the universe has truly existed forever in an infinite loop. One of the biggest challenges in studying lensed quasar echoes is the sheer difficulty of measuring tiny time delays with extreme accuracy. These delays are often just a few days, weeks, or months long, but in some cases, they could be years apart. To detect these echoes, astronomers need to monitor quasars continuously over long periods, comparing their brightness fluctuations in different images. This requires not only powerful telescopes but also an enormous amount of patience. Upcoming missions like the Euclid Telescope and the Nancy Grace Roman Space Telescope are expected to revolutionize this field by providing ultra-precise measurements of gravitational lenses. These telescopes will be able to capture fine details in quasar echoes that were previously impossible to detect, giving scientists an unprecedented view into the physics of these phenomena. But there's one final, mind-bending possibility to consider. What if quasar echoes could reveal evidence of advanced extraterrestrial civilizations? Some researchers have speculated that highly advanced alien species might manipulate gravitational lenses to send signals across the universe. If such civilizations exist, they might use lensed quasars as natural cosmic amplifiers, embedding signals in the light delays themselves. While this idea remains speculative, the fact that quasar echoes provide a unique window into the deepest parts of the universe means we should at least consider the possibility. Lensed quasar echoes are far more than just a curiosity of gravitational physics. They are cosmic keys, tools that allow us to probe everything from the nature of time and dark matter to the possibility of extra dimensions and even alien intelligence. Every echo we detect is a message from the distant past, carrying information that has traveled billions of years to reach us. And as our technology improves, these echoes may finally help us unlock the deepest secrets of the universe itself. The true power of lensed quasar echoes lies in their ability to act as cosmic laboratories for testing the fundamental laws of physics. These echoes are not just passive signals from the past. They actively reveal the nature of space, time, and the unseen forces that govern the universe. As astronomers refine their techniques for analyzing these echoes, new discoveries may challenge our deepest assumptions about reality itself. One of the most intriguing aspects of lensed quasars is their potential to serve as a natural probe of space-time curvature. General relativity tells us that massive objects warp the fabric of space-time, but could this warping behave differently under extreme conditions? Some alternative theories of gravity suggest that space-time might ripple in unexpected ways, producing subtle distortions in the time delays of lensed quasars. If scientists detect inconsistencies in the predicted versus observed delays, it could indicate the presence of unknown physics beyond Einstein's equations. This idea ties into another mind-bending concept, quantum gravity. One of the biggest mysteries in modern science is how to reconcile general relativity, which describes gravity at large scales, with quantum mechanics, which governs the behavior of particles at microscopic levels. Lensed quasars might provide an indirect way to test quantum gravity theories. If space-time is quantized at the smallest scales, tiny fluctuations could accumulate over vast cosmic distances, creating detectable anomalies in the timing of quasar echoes. Another major breakthrough that could come from studying lensed quasar echoes is a deeper understanding of cosmic voids, the vast, empty regions of space that exist between galaxy clusters. These voids make up the majority of the universe's volume, yet they remain one of the least understood structures in cosmology. By analyzing how quasar light travels through these voids, scientists might uncover hidden properties of the cosmic web, the vast interconnected structure of galaxies and dark matter that defines the large-scale universe. But what if quasar echoes could also reveal something even stranger, the possibility of alternate universes? Some versions of the multiverse theory suggest that slight variations in the fundamental constants of physics could occur in different regions of space. If a quasar's light passes through a gravitational lens located at the boundary of such a variation, it could create unexpected shifts in the observed echoes. This would be one of the first observational clues that our universe is not alone but part of a much larger, interconnected reality. Lensed quasars could also serve as powerful tools for testing one of the most perplexing questions in physics: the nature of dark energy. This mysterious force is driving the accelerated expansion of the universe, but its true nature remains unknown. Some theories propose that dark energy might not be a constant force but could fluctuate over time and space. By carefully measuring the time delays in quasar echoes, astronomers might be able to detect variations in dark energy's influence, providing critical insights into its true nature. The study of lensed quasar echoes also offers a rare opportunity to test the phenomenon of gravitational wave lensing. Gravitational waves, ripples in spacetime caused by cataclysmic cosmic events, are typically detected using ground-based observatories like LIGO and Virgo. However, if a strong gravitational lens lies between Earth and a distant quasar, it could split and delay gravitational waves just as it does with light. This means that lensed quasars could help astronomers detect gravitational wave echoes, potentially revealing events such as black hole mergers that occurred billions of years ago. Another groundbreaking application of quasar echoes is their potential role in detecting so-called primordial black holes. These hypothetical black holes are thought to have formed in the early universe, long before stars and galaxies existed. If they exist, they could account for a significant portion of dark matter. Because primordial black holes would act as gravitational lenses, they could influence quasar echoes in unique ways, causing unusual time delays that cannot be explained by normal galaxies. If detected, these echoes could provide some of the first direct evidence of primordial black holes and their role in cosmic evolution. But let's push this even further. What if lensed quasars could help us understand the ultimate fate of the universe? One possibility is that the universe will continue expanding forever, gradually cooling until it reaches a state of maximum entropy, often called the heat death scenario. However, other models suggest the universe might eventually stop expanding and collapse in a big crunch, or even oscillate in an eternal cycle of expansion and contraction. The precise way that quasar echoes change over time could help distinguish between these competing models, giving us a glimpse into the universe's long-term destiny. Even more speculative is the idea that quasar echoes might provide evidence for violations of causality, the idea that cause and effect always follow a strict sequence. Some exotic theories propose that under extreme conditions, time might loop or even reverse in small regions of space-time. If quasar echoes ever showed anomalies where later signals seemed to arrive before earlier ones, it could hint at the existence of closed time-like curves, potentially offering real-world evidence of time travel on a quantum scale. Of course, all of these possibilities hinge on the ability of scientists to collect and analyze data with extreme precision. The upcoming generation of space telescopes will play a crucial role in this endeavor. The Vera C. Rubin Observatory, set to begin operations soon, will conduct an unprecedented sky survey, capturing millions of gravitational lenses and tracking their light curves over time. Meanwhile, the James Webb Space Telescope is already providing detailed observations of distant quasars, helping astronomers refine their models of lensing effects. But what if lensed quasar echoes have already provided us with hints of new physics, and we just haven't noticed them yet? As data processing techniques improve, scientists are now able to reanalyze old observations with fresh eyes, uncovering subtle patterns that might have been overlooked. Machine learning algorithms are being trained to detect complex variations in quasar echoes, potentially revealing hidden signatures of unknown physical processes. And then there's the most profound question of all: could lensed quasar echoes challenge our entire understanding of reality? Some physicists propose that the universe might be a vast computational system, operating on principles akin to a simulation. If this idea is correct, then quasar echoes might reveal unexpected discontinuities, glitches, if you will, that could hint at the underlying structure of this cosmic code. While still highly speculative, this possibility pushes the limits of what we can learn from studying these extraordinary natural phenomena. Ultimately, lensed quasar echoes represent one of the most fascinating frontiers in modern astrophysics. They are not just beautiful cosmic mirages but powerful tools for probing the deepest mysteries of the universe. From testing the nature of time and space to uncovering dark matter, dark energy, and even hints of alternate realities, these echoes provide a rare glimpse into the unseen fabric of the cosmos. As technology advances and our ability to analyze these signals improves, who knows what groundbreaking discoveries await? The answers may be hidden in the light that has traveled billions of years to reach us, waiting to be decoded. Lensed quasar echoes might be one of the most underrated keys to unlocking the deepest secrets of the cosmos. The fact that they allow us to study gravitational lensing, measure cosmic distances, and even test the laws of physics makes them invaluable. But beyond their scientific applications, they also raise profound philosophical questions about the nature of reality itself. If light can be bent, delayed, and magnified in such extraordinary ways, what does that say about our perception of time, space, and causality? Could the very fabric of reality be more fluid and malleable than we assume? One of the biggest implications of studying lensed quasars is their ability to refine our understanding of the Hubble constant, the rate at which the universe is expanding. For decades, astronomers have struggled with an ongoing discrepancy between different methods of measuring the Hubble constant. Observations of the cosmic microwave background, the afterglow of the Big Bang, suggest one value, while measurements based on supernovae and other celestial objects suggest another. This conflict, often called the Hubble tension, remains one of the biggest mysteries in cosmology. Lensed quasars offer a completely independent way to measure cosmic expansion. Because light from a quasar is delayed by different amounts as it travels around a lensing galaxy, astronomers can use these delays to determine absolute distances with high precision. By comparing the time-delayed data with other cosmic distance measurements, scientists can refine our understanding of the universe's expansion rate. If the values from lensed quasars align with one of the existing methods, it might help resolve the Hubble tension. If they reveal an entirely new number, it could indicate that our current cosmological models need revision. But what if lensed quasar echoes are telling us something even more radical? Some scientists have proposed that the inconsistencies in measuring the Hubble constant might not just be an observational issue but a sign that dark energy is evolving over time. If dark energy is not a constant force but instead fluctuates, it could explain why different methods yield different values. Lensed quasars, by providing an independent measurement of cosmic distances and time delays, could help determine whether dark energy is truly constant or if it behaves in ways we have yet to understand. Another mind-blowing possibility is that lensed quasar echoes might provide evidence for cosmic strings, hypothetical one-dimensional defects in space-time that could have formed in the early universe. These cosmic strings, if they exist, would create unique gravitational lensing effects, producing additional distortions in the time delays of quasar echoes. If scientists detect unusual deviations in quasar echoes that cannot be explained by ordinary gravitational lensing, it could be a sign that cosmic strings are real, providing a direct window into the physics of the early universe. The search for cosmic strings ties into a much larger question. Could lensed quasars help us understand the structure of space-time at the smallest possible scales? According to some theories of quantum gravity, space-time is not perfectly smooth but instead has a fine-grained, discrete structure at extremely small scales. If this is true, light passing through a strong gravitational lens might experience tiny, random fluctuations as it travels. These fluctuations could imprint subtle but detectable patterns onto quasar echoes, potentially providing some of the first observational evidence for the quantum nature of space-time. But let's take this a step further. What if quasar echoes are more than just a tool for studying physics? What if they hint at something even deeper about the nature of the universe itself? Some scientists have proposed that reality might not be continuous but instead composed of discrete frames, much like the individual images in a film reel. In this view, time does not flow smoothly but instead jumps from one moment to the next, at a level far beyond human perception. If this hypothesis is correct, then quasar echoes, due to their extreme sensitivity to tiny variations in light, might one day reveal evidence of this hidden, frame-like structure of reality. Lensed quasar echoes also provide an exciting way to test one of the strangest ideas in theoretical physics, the holographic principle. This concept suggests that all of the information in the universe might actually be encoded on a lower-dimensional surface, much like a hologram. If this is true, then space-time itself might emerge from a deeper, more fundamental layer of reality. Some versions of this theory predict that light traveling over cosmic distances could experience tiny distortions as it interacts with this underlying holographic structure. Quasar echoes, with their extreme sensitivity to minute fluctuations in light, might be the perfect tool to test whether our universe truly behaves like a hologram. Even beyond these theoretical implications, lensed quasars could hold practical significance for the future of space exploration. If we ever develop the ability to harness gravitational lensing for observational purposes, we could use massive celestial bodies as natural telescopes to study distant exoplanets in unprecedented detail. By analyzing how quasar echoes interact with lensing effects, scientists could refine techniques for using gravitational lenses to magnify faint signals from distant worlds, potentially allowing us to detect biosignatures or even signs of extraterrestrial technology. And speaking of extraterrestrial life, could quasar echoes themselves provide indirect evidence of advanced civilizations? Some scientists have speculated that if an advanced extraterrestrial intelligence were capable of manipulating gravity on a massive scale, they might be able to create artificial gravitational lenses. These lenses could be used for interstellar communication, energy collection, or even large-scale engineering projects. If we ever detect anomalies in lensed quasar echoes that cannot be explained by natural phenomena, it might hint at the presence of artificial gravitational structures, essentially, the cosmic fingerprints of an advanced civilization. At the same time, studying lensed quasars could also help us understand more about our own place in the universe. The very fact that we can detect and analyze echoes from objects billions of light-years away is a testament to human ingenuity. It demonstrates our ability to extend our senses across vast cosmic distances, uncovering secrets that would have been unimaginable just a century ago. Every piece of data gathered from a lensed quasar represents a moment in time, a snapshot of the universe as it once was, preserved in the echoes of light that have traveled for billions of years. But perhaps the most profound realization comes from the sheer scale of what these echoes represent. The light we see from a lensed quasar is not just a random flicker in the night sky. It is a message from the distant past, a glimpse into an era long before the Earth even existed. When we study these echoes, we are looking back at a time when the universe was younger, galaxies were still forming, and cosmic evolution was in its infancy. In a way, these echoes are the closest thing we have to a time machine, allowing us to reconstruct the story of the cosmos with incredible precision. So where does this leave us? Lensed quasar echoes are not just a fascinating curiosity, they are one of the most powerful tools we have for understanding the universe. They challenge our perceptions of space, time, and reality itself. They offer insights into dark matter, dark energy, cosmic expansion, and the fundamental laws of physics. They might even hold the key to unraveling some of the deepest mysteries in theoretical physics, from quantum gravity to the multiverse. And as our ability to study these echoes improves, who knows what new discoveries await? Perhaps the greatest lesson of all is that the universe is far more complex and mysterious than we can imagine. Each lensed quasar is a window into the unknown, a reminder that the cosmos still holds countless secrets waiting to be uncovered. And as long as we keep searching, as long as we keep asking questions, we will continue to push the boundaries of what is possible, uncovering truths that will shape our understanding of reality for generations to come. One of the most fascinating aspects of lensed quasar echoes is the way they act as natural laboratories for testing Einstein's general theory of relativity. When light from a quasar passes through a massive galaxy or galaxy cluster on its way to Earth, the gravitational pull of the intervening mass bends and distorts the light, creating multiple images of the quasar. But there's something even more interesting. Each image is actually a different version of the quasar, captured at a slightly different time due to the variations in light travel distance. This time delay, known as a gravitational time delay, allows scientists to study how space-time itself warps under extreme gravitational forces. Gravitational lensing provides one of the most precise tests of Einstein's theory, and so far, every observation has confirmed its predictions with remarkable accuracy. But what if one day, a lensed quasar echo produces an unexpected result? What if we detect a time delay that cannot be explained by conventional gravitational lensing models? Such a discovery could suggest that general relativity is incomplete, or that unknown forces are at play in the universe. Some physicists believe that deviations in time delay measurements could hint at the existence of extra dimensions, predicted by theories such as string theory. If space-time has more than the familiar 4 dimensions, 3 spatial and 1 temporal, then light traveling through these additional dimensions could produce unexpected anomalies in lensed quasar echoes. This brings us to another mind-blowing implication: the possibility of detecting exotic physics beyond the Standard Model. The Standard Model of particle physics is one of the most successful scientific theories ever developed, but it has known limitations. It does not account for dark matter, dark energy, or gravity at the quantum scale. Lensed quasars, due to their extreme sensitivity to tiny variations in cosmic structure, might provide indirect evidence of unknown particles or forces that influence how light propagates through spacetime. For example, some physicists have proposed the existence of axions, hypothetical ultralight particles that could explain dark matter. If axions exist, they could subtly alter the way light behaves when passing through strong gravitational fields. By studying the fine details of lensed quasar echoes, scientists might be able to detect signatures of axion-like particles, shedding light on one of the biggest mysteries in modern physics. And speaking of dark matter, lensed quasars offer one of the most promising ways to map its distribution. Dark matter is invisible. It does not emit, absorb, or reflect light, but its gravitational influence affects how light from distant quasars is bent. By carefully analyzing the distortions in quasar echoes, astronomers can create high-resolution maps of dark matter structures, revealing their shape, density, and evolution over cosmic time. This technique, known as gravitational lensing tomography, is one of the few methods available to directly study the invisible scaffolding of the universe. But what if the lensing effects we observe are not just caused by dark matter, but by something even stranger? Some theories propose that space-time itself might contain hidden, undetectable structures, fluctuations in the vacuum energy that could subtly alter how light travels across vast cosmic distances. If true, lensed quasar echoes could serve as a tool for detecting these hidden features, providing evidence for new physics that goes beyond our current understanding. Another frontier in lensed quasar research is the search for rogue black holes, massive black holes that are not anchored to a galaxy but instead drift freely through intergalactic space. These objects are nearly impossible to detect directly, but they could reveal themselves through their gravitational lensing effects on distant quasars. If a rogue black hole happens to pass in front of a quasar, it could create a sudden and dramatic change in the quasar's brightness, producing a unique type of quasar echo. Detecting such an event would provide the first direct evidence of rogue black holes, confirming their existence, and helping us understand how they form and evolve. Even more intriguing is the possibility that lensed quasar echoes could be used to test one of the most controversial ideas in physics, the simulation hypothesis. This idea, popularized by thinkers like Nick Bostrom and Elon Musk, suggests that our reality might be an advanced computer simulation. If the universe is a simulation, then it might have built-in limitations, subtle glitches or irregularities in the fabric of space-time. Some physicists have speculated that if we are living in a simulation, then the fine structure of quasar echoes could reveal unexpected anomalies, patterns that do not conform to known physical laws. While this idea remains speculative, it highlights just how deeply lensed quasars challenge our understanding of the nature of reality. But let's bring things back to a more practical level. One of the most exciting applications of lensed quasar echoes is their role in improving astronomical timekeeping. By precisely measuring the delays in quasar echoes, scientists can refine our understanding of cosmic time, improving our ability to synchronize observations across different telescopes and missions. This is particularly important for upcoming space observatories like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, both of which will rely on precise time delay measurements to study dark energy and the expansion of the universe. Lensed quasars also provide crucial insights into the intergalactic medium, the vast, diffuse gas that fills the space between galaxies. As light from a quasar travels across billions of light-years, it passes through clouds of gas, absorbing and re-emitting energy in complex ways. By analyzing the spectral signatures of quasar echoes, astronomers can map the composition, temperature, and movement of intergalactic gas, providing clues about the large-scale structure of the universe. And there's still so much more to explore. What happens when a quasar lensing event coincides with other extreme cosmic events, like a supernova or a gamma-ray burst? Could the combination of multiple transient phenomena create unique observational signatures that reveal new aspects of astrophysics? Could lensed quasars help us detect hypothetical objects like primordial black holes, which may have formed in the first moments after the Big Bang? The more we study lensed quasar echoes, the more questions arise. Each observation pushes the boundaries of what we know, opening new doors to discoveries that could revolutionize our understanding of the cosmos. Whether it's refining our measurements of cosmic expansion, probing the nature of dark matter, testing fundamental physics, or even exploring the limits of reality itself, lensed quasars stand at the frontier of modern astrophysics. In the coming decades, as next-generation telescopes come online, such as the Vera C. Rubin Observatory, the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, our ability to study lensed quasars will reach unprecedented levels. With higher resolution, greater sensitivity, and improved computational models, we may finally be able to answer some of the deepest questions in science. But until then, every lensed quasar echo serves as a reminder of how much we still have to learn. Each flicker of light, delayed and distorted by the vast cosmic landscape, carries within it the story of the universe itself. And as long as we keep listening to these echoes, who knows what secrets they will reveal? One of the most intriguing aspects of lensed quasar echoes is how they can be used to measure the Hubble constant, the rate at which the universe is expanding. This is a huge deal because there is an ongoing crisis in cosmology known as the Hubble tension. When scientists measure the expansion rate of the universe using different methods, they get conflicting results. Observations of the early universe, like those from the cosmic microwave background, suggest one value, while direct measurements using supernovae and Cepheid variable stars suggest another. Lensed quasar echoes provide a completely independent method for measuring cosmic expansion. Since each lensed image of a quasar appears at a different time due to gravitational lensing delays, scientists can use these time delays, combined with lensing models, to determine the Hubble constant. If this method confirms one of the existing measurements, it could resolve the tension. But if it gives yet another conflicting result, it would suggest something is fundamentally wrong with our understanding of the cosmos. Maybe new physics is needed to explain it. Another incredible use of lensed quasar echoes is the ability to detect microlensing effects from individual stars within the lensing galaxy. Normally, when we talk about gravitational lensing, we think of an entire galaxy or a massive cluster bending light. But within these galaxies, there are countless stars, and each of them exerts its own tiny gravitational pull. When light from a quasar passes through the lensing galaxy, individual stars can create tiny fluctuations in brightness as they act as miniature gravitational lenses. This phenomenon, known as microlensing, allows scientists to study objects that would otherwise be completely invisible, like rogue planets, stellar mass black holes, and even hypothetical objects like primordial black holes. If primordial black holes exist, they could be a major component of dark matter, so detecting them through quasar microlensing would be a groundbreaking discovery. But let's take a step back and talk about something even stranger. Could lensed quasar echoes be used to test whether the speed of light has always been constant? According to standard physics, the speed of light in a vacuum is a fundamental constant of nature. But some alternative theories suggest that in the very early universe, light may have traveled at different speeds due to exotic physical conditions. If this were true, we might be able to detect subtle variations in the arrival times of quasar echoes that do not match standard gravitational lensing models. If scientists ever find such anomalies, it could force us to rethink our understanding of space, time, and the fundamental forces that govern the universe. Now, let's explore another mind-bending possibility, using lensed quasars to detect cosmic strings. Cosmic strings are hypothetical, ultra-thin, one-dimensional defects in space-time that may have formed in the early universe. If they exist, they would be incredibly massive and could act as gravitational lenses, warping light in unique and detectable ways. Unlike traditional gravitational lenses like galaxies, cosmic strings would produce sharp, nearly identical duplicate images of quasars, with no time delay between them. If astronomers ever detect a quasar echo with these characteristics, it could be the first direct evidence of cosmic strings, providing a window into the physics of the early universe. But we're not done yet. Lensed quasar echoes may also help us understand the mysterious phenomenon of fast radio bursts, FRBs. FRBs are extremely powerful but short-lived bursts of radio waves from unknown sources. Some theories suggest that FRBs could be linked to magnetars, highly magnetized neutron stars, while others propose more exotic explanations, like energy leakage from advanced alien civilizations. If an FRB happens to pass through a gravitational lens, it could create multiple delayed echoes, just like a quasar. Detecting such an event would allow scientists to pinpoint the source of an FRB and determine whether its origin is natural or something more unusual. Speaking of unusual, what if lensed quasars could be used to test the hypothesis that black holes have hair? According to classical general relativity, black holes are extremely simple objects described only by their mass, spin, and charge. This idea is known as the no-hair theorem. However, some alternative theories suggest that black holes could have additional features, subtle structures or hair, that could influence how they interact with surrounding spacetime. By carefully studying the gravitational lensing effects of quasars around supermassive black holes, scientists might be able to detect tiny deviations from the predictions of general relativity, providing evidence that black holes are more complex than we thought. Another bizarre but fascinating possibility is that lensed quasar echoes could be used to search for evidence of a cyclic universe. Some cosmological theories propose that the universe undergoes an endless series of expansions and contractions, big bangs followed by big crunches. If this were true, then some light traveling across the cosmos could have been echoed from a previous cycle of the universe, passing through lensing structures that have existed for eons. While this idea remains highly speculative, if any quasar echoes exhibit properties that cannot be explained by conventional physics, it might be worth considering whether they could be remnants of an earlier cosmic epoch. And let's not forget one of the most practical applications of lensed quasar echoes, improving the precision of gravitational wave astronomy. Gravitational waves, ripples in spacetime caused by massive cosmic events like black hole mergers, are an exciting new tool for studying the universe. However, detecting them and pinpointing their sources is extremely difficult. If a gravitational wave event occurs in the same region as a lensed quasar, the time delays from the quasar echo could help refine the measurements of gravitational wave signals, improving our ability to locate and study these cosmic ripples. With all these incredible implications, it's clear that lensed quasar echoes are far more than just an astronomical curiosity. They are a powerful tool for probing the very fabric of the universe, revealing secrets about dark matter, black holes, the early cosmos, and even the fundamental nature of reality itself. As technology advances, new telescopes like the James Webb Space Telescope, JWST, the Vera C. Rubin Observatory, and the European Space Agency's Euclid mission will provide even more detailed observations of lensed quasars. With higher resolution and better data, we may finally unlock some of the deepest mysteries of the cosmos. Will we find evidence of new physics? Will we uncover hidden structures in space-time? Will we detect the echoes of a past universe? The answers may lie in the flickering light of a quasar, bent and distorted by the invisible forces of the cosmos. One of the most fascinating aspects of lensed quasar echoes is their potential to reveal the true nature of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, but we still don't know what it actually is. Is it a constant energy embedded in space itself, like Einstein's cosmological constant? Or is it some kind of evolving field that changes over time? If dark energy isn't a constant, then the way lensed quasars appear to us could subtly change depending on how far back in time we're looking. By analyzing the distribution and timing of quasar echoes across different cosmic epochs, we might be able to detect variations in dark energy that could confirm whether it's truly constant or something more dynamic. But that's just one piece of the puzzle. Another intriguing possibility is using lensed quasars to test whether the universe is truly homogeneous on the largest scales. The standard model of cosmology assumes that, on average, the universe looks the same in all directions. However, there have been some observations that suggest otherwise. Certain cosmic structures appear to be larger than what should be possible under standard physics, and some studies hint at an anisotropic universe, meaning it might expand differently in different directions. If this is true, then the time delays between lensed quasar images might not be the same in all regions of the sky. By carefully mapping out these variations, we could potentially detect large-scale cosmic structures or even anisotropies that challenge our current understanding of the cosmos. And speaking of cosmic structures, there's another mind-bending question we can explore. Could lensed quasar echoes help us detect wormholes? Wormholes, hypothetical shortcuts through space-time, are a favorite of science fiction, but some physicists believe they could actually exist. If a quasar's light passed through a wormhole rather than being bent by a normal gravitational lens, the resulting echoes might show unusual time delays that don't match conventional lensing models. Even more bizarre, some wormhole theories predict that a signal could travel through them faster than light would normally travel through regular space. If a quasar's light took an unexpected shortcut, it could create echoes that appear at seemingly impossible times, potentially revealing the presence of a wormhole. So far, no definitive evidence for wormholes has been found, but the search continues. Now, let's turn our attention to something equally strange: whether lensed quasar echoes could help us test the idea of variable fundamental constants. In physics, there are a handful of fundamental constants that are assumed to be unchanging, like the speed of light, the gravitational constant, and the fine structure constant, which determines the strength of electromagnetic interactions. But what if these constants aren't actually constant? Some theories propose that in extreme conditions, such as the very early universe or around strong gravitational fields, these constants might shift slightly. If that's true, then light from distant quasars, which has traveled across billions of years, could carry the fingerprints of these changes. By studying how the echoes of lensed quasars behave in different regions of the universe, scientists might be able to detect tiny variations in fundamental constants that could revolutionize our understanding of physics. But let's take things even further. Could lensed quasar echoes help us test the simulation hypothesis? This is the idea that our entire universe might be a highly advanced simulation, like a cosmic-scale version of a video game. Some versions of this theory suggest that tiny glitches or inconsistencies in physics might appear at the deepest levels of reality, possibly detectable in astronomical observations. If quasar echoes exhibit patterns that don't align with any known physics, one radical interpretation could be that we're seeing evidence of an underlying computational framework, an artifact of the simulated nature of our universe. While this is highly speculative, some physicists have argued that subtle anomalies in gravitational lensing, cosmic background radiation, or quantum fluctuations might provide indirect clues. If anything were to hint at this possibility, lensed quasars could be one of the best places to look. Another bizarre but scientifically meaningful idea is using lensed quasar echoes to probe the possibility of extra dimensions. Some advanced physics theories, such as string theory, propose that our universe might have more than the three spatial dimensions we experience. These extra dimensions could be incredibly tiny or hidden in ways we can't directly perceive. However, if they influence gravity in subtle ways, they might leave an imprint on the way light bends around massive objects. If lensed quasar echoes show unexpected distortions that don't fit into our current models of gravity, it could hint at the existence of hidden dimensions shaping our universe in ways we never imagined. And what about the possibility of detecting alien megastructures? Some researchers have speculated that highly advanced civilizations could build massive structures around stars or even entire galaxies to harness energy. If such a structure happened to be in the line of sight of a lensed quasar, its gravitational influence could alter the expected time delays in ways that don't match any known natural lensing object. While there's no confirmed evidence for such megastructures, the search for anomalies in quasar echoes could provide a new method for looking for advanced extraterrestrial activity on a cosmic scale. But let's bring things back to more grounded physics for a moment, specifically, how lensed quasars could help refine our understanding of general relativity itself. Einstein's theory has passed every test we've thrown at it so far, but we know it doesn't fully describe the universe, especially when it comes to uniting gravity with quantum mechanics. If quasar echoes reveal tiny deviations from what general relativity predicts, it could hint at new physics beyond Einstein. In fact, some alternative gravity theories propose that space-time might behave differently at extremely large cosmic scales, and lensed quasars provide a perfect natural laboratory to test these ideas. On top of all that, lensed quasar echoes are also proving to be an invaluable tool for calibrating future space telescopes. Instruments like the upcoming Nancy Grace Roman Space Telescope and other next-generation observatories will rely on extremely precise measurements of cosmic distances and gravitational lensing effects. By studying quasar echoes now, scientists are building a foundation that will improve the accuracy of these future missions, helping us unlock even more secrets of the cosmos. So, what's next for this field of study? As observational technology advances, astronomers are aiming to discover even more lensed quasars and measure their echoes with greater precision. Some researchers are also developing machine learning algorithms to analyze massive datasets of quasar light curves, allowing them to detect subtle variations that the human eye might miss. The more we refine our techniques, the more we'll be able to push the boundaries of what we can learn from these cosmic beacons. Lensed quasar echoes are not just another astronomical curiosity. They are a gateway to understanding some of the deepest questions about the universe. They provide a natural time machine that lets us test fundamental physics, explore the nature of space-time, and even search for the extraordinary, from hidden dimensions to alien technology. Every flicker of light from a distant quasar carries a story written across billions of years, bent and echoed by the vast structures of the cosmos. And as we continue to study these echoes, we may find that they don't just reveal the history of the universe. They may redefine our understanding of reality itself. It's incredible to think that something as simple as light, traveling across billions of years, can carry within it the secrets of the cosmos. But the study of lensed quasar echoes is proving to be one of the most powerful tools in modern astrophysics. We've already covered how they help us measure cosmic expansion, test dark matter theories, and even probe the possibility of exotic physics. But there are still deeper layers to this mystery, each revealing more about the universe than we ever thought possible. One of the most exciting aspects of lensed quasars is their role in testing the limits of quantum gravity. Right now, general relativity and quantum mechanics work beautifully in their own domains. Relativity explains gravity on large scales, while quantum mechanics governs the smallest particles in the universe. But when we try to combine them into one theory, things break down. Some researchers believe that studying the way light from lensed quasars is affected by extreme gravitational environments could provide clues about how gravity behaves at quantum scales. For example, some quantum gravity theories predict that space-time itself isn't perfectly smooth but has a foamy, jittery structure at incredibly small scales. If this is true, then the light traveling from distant quasars should experience tiny fluctuations as it moves through this quantum foam. These fluctuations might show up in the time delays of lensed quasar echoes, creating patterns that don't match classical physics. If detected, this would be one of the biggest breakthroughs in modern physics, giving us direct evidence of quantum effects on space-time itself. But let's take it even further. Could lensed quasars help us solve the black hole information paradox? This is one of the most perplexing problems in physics. According to general relativity, anything that falls into a black hole is lost forever. But quantum mechanics says information can't be destroyed. So what happens to the information of something that falls into a black hole? Some theories suggest that black holes might leave behind a subtle imprint on the fabric of space-time itself, possibly altering the paths of light that passes nearby. By analyzing the way quasar light is bent around galaxies that might host massive black holes, scientists could look for tiny discrepancies that might hint at a deeper resolution to the paradox. And speaking of black holes, lensed quasar echoes could also provide a way to detect so-called naked singularities. In Einstein's theory, a singularity is a point where gravity becomes infinite, like the center of a black hole. Normally, these singularities are hidden behind an event horizon, meaning no information can escape. But some alternative theories suggest that in certain conditions, singularities could exist without an event horizon, meaning they'd be visible to the outside universe. If that's true, they would distort light in ways that no known object should, and quasar echoes could reveal their presence. This would be a direct violation of the cosmic censorship conjecture, a principle that suggests nature should always hide singularities behind horizons. If we find evidence of naked singularities, it could force us to completely rethink our understanding of gravity. Now, let's talk about another way lensed quasars are being used to push the boundaries of physics, by testing the speed of gravity itself. According to general relativity, gravitational waves should travel at the speed of light. But if gravity behaves differently at cosmic scales, there could be tiny deviations from this prediction. One way to test this is by looking at the arrival times of gravitational waves from distant cosmic events compared to the light echoes from lensed quasars. If we ever detect a mismatch, it could be a sign that gravity isn't quite what we think it is. And what about the possibility of detecting cosmic strings? Cosmic strings are hypothetical, one-dimensional defects in space-time that might have formed in the early universe. These objects would be thinner than an atom but could stretch across the entire universe, warping space-time around them. If a quasar's light passes near one of these cosmic strings, it would create a very specific kind of lensing effect, causing echoes that appear slightly different from those created by normal galaxies. Finding even one cosmic string would be groundbreaking. It would confirm theories about phase transitions in the early universe and potentially give us clues about what happened during the first fractions of a second after the Big Bang. Let's take a step back and think about just how powerful these tiny fluctuations of light really are. Every time we observe a lensed quasar echo, we're not just looking at a distant object, we're peering through a time machine that carries information about the universe's past. Some of the light we see has been traveling for billions of years, bending around galaxies, encountering dark matter, possibly interacting with unknown forces, before finally reaching us. By decoding these signals, we're essentially reading the history of the universe itself. But the journey doesn't end here. Future advancements in telescopes and AI-powered data analysis are going to supercharge our ability to study lensed quasars. The upcoming Vera C. Rubin Observatory, set to begin operations soon, will scan the entire sky every few nights, capturing more transient cosmic events than ever before. This will allow us to detect thousands of new lensed quasars and their echoes, vastly increasing our dataset and refining our models. Even more exciting is the potential for space-based telescopes, like the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope, to provide high-resolution images of these lensing events. With sharper data, we'll be able to see finer details in the light curves of quasar echoes, allowing us to make even more precise measurements of cosmic expansion, dark matter distribution, and potentially new physics beyond what we currently understand. So, what does all of this mean for the future of astrophysics? If we continue to refine our observations of lensed quasar echoes, we might soon be able to settle some of the biggest debates in cosmology. Is dark energy truly constant, or is it evolving over time? Is dark matter really made of weakly interacting particles, or is there something even more exotic at play? Could we finally bridge the gap between quantum mechanics and general relativity? These are not just abstract scientific questions. They are fundamental to understanding the nature of reality itself. And perhaps the most exciting thought of all, what if we find something completely unexpected? Throughout history, some of the biggest scientific breakthroughs have come not from confirming what we already expected but from discovering something totally new. If quasar echoes reveal anomalies that don't fit into our current models, they could be pointing us toward a revolution in physics, a new way of thinking about the universe that we haven't even imagined yet. With every new lens quasar we discover, we are uncovering another layer of the cosmic story, peeling back the mysteries of space-time, and stepping closer to answers that have eluded us for centuries. Whether it's testing fundamental physics, searching for evidence of hidden cosmic structures, or even detecting signs of intelligent life, the echoes of distant quasars may hold the key to the greatest discoveries yet to come. And that's why this topic is so important. Lensed quasar echoes aren't just an interesting quirk of astrophysics. They're one of the most powerful tools we have for unlocking the deepest secrets of the universe. They remind us that the cosmos is far stranger and more complex than we ever imagined, and that every flicker of light, no matter how distant, carries with it the potential to change everything we know about reality. Lensed quasar echoes are one of the most remarkable cosmic signals we have ever detected. They represent a natural experiment conducted by the universe itself, allowing us to study how light bends, how time stretches, and how hidden structures influence what we see. These echoes provide us with data from deep in the past, carrying with them an unbroken record of billions of years of cosmic history. But beyond being a fascinating phenomenon, they also serve as a crucial tool for answering some of the biggest open questions in astrophysics. One of the most fascinating aspects of lensed quasars is how they reveal the structure of time delays and gravitational lensing. When light from a distant quasar is bent by an intervening galaxy, it takes multiple paths to reach us. Some of these paths are shorter and more direct, while others are longer and take extra time. This means that when the quasar undergoes a brightening event, such as an eruption caused by activity around its central supermassive black hole, we don't see that flash just once. Instead, we see it repeated at different times, sometimes days, weeks, months, or even years apart, depending on the gravitational lens's configuration. These repeated flashes are what we call lensed quasar echoes. But why does this matter? Because these echoes allow us to measure one of the most important numbers in cosmology, the Hubble constant. The Hubble constant describes how fast the universe is expanding. The problem is, scientists currently have two different measurements that don't agree with each other. One based on the cosmic microwave background radiation and another based on supernova observations. This is known as the Hubble tension, and it's a major mystery in astrophysics. Lensed quasar echoes offer a completely independent way to measure the Hubble constant. By carefully analyzing the time delays between the multiple images of a quasar, astronomers can determine the absolute distance to the quasar and use that to refine their calculations of cosmic expansion. If the results from lensed quasars match one of the existing measurements, it could help resolve the Hubble tension. But if they don't match either, it could mean that our entire understanding of cosmic expansion needs to be rethought. Another key role of lensed quasar echoes is their ability to reveal the distribution of dark matter. We know dark matter is there because of its gravitational effects, but we still don't know what it actually is. One of the best ways to study it is through gravitational lensing, because the way light bends around galaxies is influenced by both visible and dark matter. Now, most galaxies are surrounded by an invisible halo of dark matter. The exact shape and structure of these halos are still unknown. However, by studying how the light from quasars gets bent and delayed by these halos, astronomers can map out their distribution in incredible detail. Lens quasar echoes, in particular, give us a time-dependent way of studying these effects, allowing us to see how dark matter might be clumped or moving over time. And here's where things get even more interesting. Some theories suggest that dark matter might not be entirely smooth. Instead, it could form tiny clumps or filaments, like an invisible cosmic web stretching across the universe. If that's true, then quasar echoes should sometimes show small, unexpected deviations in their timing or brightness, caused by these invisible dark matter structures subtly altering the paths of the light. Detecting these tiny fluctuations would give us our first direct clue about the small-scale behavior of dark matter. But there's another layer to this. Some alternative theories propose that dark matter might be made of something even stranger, like axions, hypothetical ultralight particles that could form wave-like structures instead of particle-like clumps. If axions exist, they could create interference patterns in the lensing effect, subtly shifting the arrival times of quasar echoes in ways that standard dark matter models wouldn't predict. If we ever detect these patterns, it could revolutionize our understanding of dark matter and possibly even lead to new physics beyond the standard model. Now, let's take this concept even further. Could lens quasar echoes help us test exotic theories of gravity? We already mentioned how they could be used to test the speed of gravity, but there's another possibility. They could provide a way to detect deviations from Einstein's general relativity itself. Some alternative theories of gravity predict that spacetime is not perfectly smooth but has additional geometric properties that only become apparent over vast distances. If that's the case, then the way light from a quasar bends around a galaxy should exhibit slight deviations from what standard general relativity predicts. These deviations could be imprinted in the structure of quasar echoes, revealing whether or not gravity behaves differently on cosmic scales. One particular area where this could be crucial is in testing the idea of fifth forces, unknown forces beyond the four fundamental ones we currently know: gravity, electromagnetism, the weak force, and the strong force. Some theories suggest that a new, ultra-weak force might be acting on cosmic scales, subtly influencing how galaxies and quasars interact. If such a force exists, it could cause very slight shifts in the time delays of lens quasar echoes. Detecting these shifts could be the first sign that there's an entirely new force in nature waiting to be discovered. But the implications of lens quasars don't stop at dark matter, dark energy, or gravity. There's also the possibility that they could help us detect hidden cosmic structures, things that exist but are otherwise invisible to us. One of the most intriguing possibilities is that they could reveal the presence of ancient cosmic strings. Cosmic strings are hypothetical one-dimensional defects in spacetime that could have formed in the early universe. These structures would be incredibly thin, possibly even thinner than a proton, but they could stretch across the entire universe and have enormous gravitational effects. If a quasar's light passes near a cosmic string, it would create a unique lensing signature that would show up in the echoes. By searching for these anomalies, we might be able to find evidence of cosmic strings, which would be a groundbreaking discovery about the early universe's formation. And then there's the truly mind-bending idea: could lens quasar echoes help us detect signs of advanced alien civilizations? If an advanced civilization had the capability to manipulate gravity, say, by constructing massive artificial structures around black holes or using gravitational lensing for their own observational purposes, it might leave behind detectable imprints in quasar echoes. Some researchers have speculated that highly advanced civilizations could use gravitational lensing to send signals across the universe, utilizing natural lenses like galaxies to magnify their transmissions. If that's happening, then lens quasar echoes might contain signatures that don't fit any natural explanation. Imagine that we find an unexpected delay pattern in a quasar echo, something that doesn't match any known gravitational lensing effect, dark matter structure, or cosmic phenomenon. If we can't explain it using physics, it might mean that something, or someone, is deliberately altering the signal. While this is still purely speculative, the idea that lens quasar echoes could one day be used to search for intelligent signals is an exciting possibility that could redefine our understanding of life in the universe. Lens quasar echoes are much more than a fascinating curiosity. They are a window into the fundamental nature of reality itself. They help us measure cosmic expansion, map the invisible structures of the universe, test the nature of dark matter and dark energy, and even probe the possibility of new physics. And perhaps, just perhaps, they might one day reveal something so unexpected that it changes everything we thought we knew about the universe. Lensed quasar echoes provide an extraordinary opportunity to probe the very fabric of space-time. One of the most profound questions in physics is whether space-time itself is smooth or if it exhibits tiny, quantum-level fluctuations. According to some theories, space-time might not be a continuous sheet but instead have a discrete, granular structure at the smallest scales. These ideas are central to quantum gravity, a field that attempts to unify Einstein's general relativity with quantum mechanics. If space-time has a quantum structure, then light traveling vast cosmic distances should experience minuscule deviations caused by these underlying quantum fluctuations. Lensed quasar echoes could provide a way to test for this effect. When light from a quasar takes multiple paths through a gravitational lens, any inconsistencies in arrival times that can't be explained by standard physics might hint at a deeper, underlying structure of spacetime. If such deviations are detected, it could be the first observational evidence of quantum gravity in action. Another major question that lensed quasar echoes could help answer is whether gravity itself changes over vast cosmic distances. Some alternative theories of gravity suggest that at extremely large scales, general relativity may not hold exactly as we expect. If true, this could change how we interpret dark energy, the mysterious force driving the accelerated expansion of the universe. One of the ways to test for deviations in gravity is to study the precise time delays between multiple images of a quasar in a gravitational lens. If the observed delays differ slightly from what general relativity predicts, it could indicate that gravity behaves differently on cosmological scales. This would be an earth-shattering discovery because it might imply that dark energy isn't needed to explain cosmic acceleration. Perhaps gravity itself simply works differently at these scales. But lensed quasars do more than just probe fundamental physics. They also serve as cosmic laboratories for understanding the most powerful objects in the universe, supermassive black holes. Every quasar is powered by a supermassive black hole millions or even billions of times the mass of the Sun. As matter spirals into these black holes, it forms an accretion disk, a superheated ring of gas that glows brightly across the electromagnetic spectrum. However, the detailed physics of how these disks evolve is still not fully understood. Lensed quasar echoes give us a way to watch these accretion disks in action, almost like having a slow-motion replay of cosmic events. When a quasar flares due to changes in its accretion disk, we see the same flare repeated at different times due to gravitational lensing. This means we can study how the brightness of the quasar evolves over time with an unprecedented level of precision. If the flares change in a way that doesn't match existing theories, it could indicate new physics at play in the extreme environments near black holes. There's another key reason why lensed quasar echoes are important. They help us refine our models of the intergalactic medium, the vast, mostly empty space between galaxies that is filled with tenuous gas and cosmic radiation. Light from distant quasars travels through this medium for billions of years before reaching us, and in doing so, it interacts with the gas and dust along the way. By analyzing the subtle differences in brightness and color between multiple images of a lensed quasar, astronomers can map out variations in the intergalactic medium with unprecedented detail. This allows scientists to study how the universe's large-scale structure has evolved over time, revealing insights into how galaxies form and how matter is distributed on the grandest scales. And here's where things take an even wilder turn. Lensed quasar echoes might also be used to detect so-called cosmic voids, the vast empty regions in space that contain very few galaxies. These voids are an essential piece of the cosmic puzzle because their distribution and size provide key clues about the evolution of the universe. By studying how light from a quasar is affected by passing through a void, scientists can infer properties about the expansion of space itself. Even more intriguingly, some researchers have speculated that cosmic voids could be influenced by exotic forms of dark energy that vary in strength depending on location. If that's the case, then lensed quasar echoes might reveal subtle anomalies in the way quasar light is delayed and distorted, potentially giving us new insights into the mysterious nature of dark energy. But perhaps one of the most unexpected possibilities is that lensed quasar echoes could be used to test for the existence of hypothetical mirror worlds. Some theories in physics propose that there could be hidden sectors of the universe, parallel versions of our own reality that interact with our world only through gravity. If these mirror worlds exist, they could subtly alter the way gravitational lensing works, creating anomalies in the time delays of lensed quasar echoes. If we ever detect these anomalies, it could be the first sign that our universe is part of a much larger, more complex multiverse. And if that wasn't mind-blowing enough, there's even speculation that lensed quasars might one day help us search for evidence of cosmic engineering. Some researchers have wondered whether extremely advanced civilizations, if they exist, could manipulate gravitational lensing for their own purposes. For example, they might use massive artificial structures to enhance or redirect light from distant galaxies, effectively creating artificial lenses in space. If such artificial gravitational lenses exist, they would leave behind distinct, unnatural signatures in the echoes of lensed quasars. Unusual timing patterns or deviations from expected gravitational effects could indicate the presence of massive engineered structures that no natural process could explain. While this idea remains speculative, the possibility that lensed quasar echoes could one day reveal signs of intelligent manipulation is a tantalizing thought. In the grand scheme of things, lensed quasar echoes are far more than just an interesting astrophysical curiosity. They are a powerful tool that allows us to probe the deepest mysteries of the universe. Whether it's testing theories of dark matter, measuring cosmic expansion, studying black hole physics, mapping the intergalactic medium, or even searching for signs of new physics, these echoes represent one of the most valuable sources of information we have. And perhaps the most exciting part? We've barely scratched the surface of what they can teach us. As our observational techniques improve and new telescopes come online, we will uncover even more secrets hidden within these cosmic echoes. The universe is speaking to us through the light of distant quasars, and we are just beginning to learn how to listen. Lensed quasar echoes are not just a scientific curiosity, they are one of the most powerful natural experiments the universe has given us. Every quasar that gets lensed by a massive galaxy or galaxy cluster acts as a cosmic beacon, sending out duplicate images of itself across the fabric of space-time. These multiple images don't just give us a snapshot of the universe, they offer a dynamic, evolving picture of how the cosmos behaves over vast timescales. One of the most fascinating aspects of lensed quasars is that they serve as precise cosmic clocks. Because the different images of a quasar reach us at different times, we can use them to measure time delays with extraordinary precision. These time delays, when combined with our understanding of the lensing galaxy's mass distribution, allow us to measure the Hubble constant, the rate at which the universe is expanding. This is particularly crucial because different methods of measuring the Hubble constant have led to conflicting results. Currently, there is a major tension in cosmology. The measurements from the cosmic microwave background (CMB) radiation, light from the early universe, suggest a slower expansion rate than the measurements taken from supernovae and local galaxies. This discrepancy, known as the Hubble tension, could indicate that our understanding of the universe is incomplete. Lensed quasar echoes provide an independent method of measuring the Hubble constant, free from many of the systematic uncertainties that affect other methods. If these measurements confirm one side of the debate, it could reshape our entire understanding of the cosmos. Beyond measuring the expansion of the universe, lensed quasar echoes also allow us to probe the nature of dark matter with remarkable precision. Dark matter makes up about 85% of the total mass of the universe, yet it doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational effects on visible matter, light, and the large-scale structure of the universe. But what exactly is dark matter? Is it made of weakly interacting massive particles, WIMPs? Could it be a collection of ultralight axions? Or is it something even stranger, like primordial black holes or exotic new particles? Lensed quasar echoes provide a unique way to test different dark matter theories. If dark matter consists of clumpy, discrete structures, then light from a quasar should experience tiny, random deviations as it passes through these clumps. This would result in subtle variations in the light curves of different lensed images. On the other hand, if dark matter is more smoothly distributed, we should see different effects in the time delays and magnification patterns. By studying these variations, scientists can place strong constraints on the properties of dark matter, something that no particle accelerator on Earth has been able to do. Another area where lensed quasar echoes offer incredible insights is in the detection of rogue black holes. The universe is filled with black holes, but most of them are nearly impossible to detect because they don't emit light. However, if a rogue black hole happens to drift in front of a quasar, it can act as a tiny, temporary lens, distorting the light in a very specific way. By carefully analyzing the brightness variations of lensed quasar echoes, scientists can identify such rogue black holes and even estimate their masses. This could be one of the only ways we ever detect isolated black holes that are otherwise completely invisible to us. But the impact of lensed quasar echoes goes even further. They could help us test one of the most mind-bending ideas in theoretical physics: the existence of extra dimensions. Some versions of string theory suggest that our universe has more than the 3 spatial dimensions we experience. These extra dimensions, if they exist, could subtly alter the way gravity works over cosmic distances. If that's the case, then the time delays in lensed quasar echoes might not match what we expect based on general relativity alone. By comparing observed time delays with theoretical models, scientists could look for discrepancies that hint at new physics. If extra dimensions are affecting gravity, we might see strange anomalies in the lensing effects, such as unexpected shifts in arrival times or unusual distortions in the quasar images. Discovering evidence of extra dimensions would be one of the most revolutionary breakthroughs in modern physics, fundamentally changing our understanding of the universe. There's also the intriguing possibility that lensed quasar echoes could help us detect cosmic strings, hypothetical defects in spacetime that may have formed in the early universe. If cosmic strings exist, they would create highly unusual lensing effects, producing double images of quasars with identical brightness and spectra. No natural astrophysical object can mimic this behavior, so if we ever detect such an effect in lensed quasar echoes, it could provide direct evidence for these strange, hypothetical structures. As if all of this wasn't already mind-blowing, lensed quasar echoes also provide an opportunity to test whether the speed of light has truly remained constant throughout cosmic history. Some alternative theories of physics suggest that the speed of light might have been slightly different in the early universe. If this were true, it would affect the time delays between the images of a lensed quasar. By measuring these delays with extreme precision, scientists can test whether light has always traveled at the same speed or whether it has changed over time. If variations are detected, it would shake the very foundations of physics. Lensed quasars are also important for understanding the environments in which they exist. Every quasar is surrounded by a host galaxy, but these host galaxies can be difficult to study because the quasar itself is so bright. However, when a quasar is lensed, the multiple images allow astronomers to separate the light from the quasar and its host galaxy more easily. This helps us study how quasars evolve, how they interact with their surroundings, and how supermassive black holes influence the galaxies they reside in. And let's not forget one of the most practical uses of lensed quasar echoes: refining our models of gravitational lensing itself. Every time we observe a new lensed quasar system, we gain a better understanding of how matter is distributed in lensing galaxies. This, in turn, helps us improve the accuracy of lensing-based measurements in other areas of astronomy, such as the study of dark energy, galaxy evolution, and the cosmic microwave background. Ultimately, lensed quasar echoes are one of the most versatile tools in modern astrophysics. They allow us to test theories of gravity, measure cosmic expansion, probe the nature of dark matter, detect rogue black holes, search for extra dimensions, and even hunt for evidence of exotic physics. The sheer amount of information contained within these gravitationally lensed light echoes is staggering, and we are only just beginning to unlock their full potential. As new telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope come online, the number of known lensed quasars is expected to increase dramatically. This means that in the coming years, we will have an unprecedented opportunity to refine our understanding of the universe using these natural cosmic laboratories. The universe has hidden so many secrets in the light of distant quasars, bending and distorting them through the vast cosmic landscape. But by studying these echoes, we are slowly learning to decode the messages imprinted on them. Each time we discover a new lens quasar, we are opening another window into the fundamental workings of reality itself. And perhaps, in the not-too-distant future, these echoes will lead us to answers that reshape everything we think we know about space, time, and the nature of existence. Lensed quasar echoes are not just a tool for measuring cosmic distances or refining our understanding of dark matter. They could also be one of the best ways to detect the most mysterious and elusive objects in the universe. Some theories suggest that primordial black holes, which formed in the first fraction of a second after the Big Bang, could make up a portion of dark matter. Unlike the stellar mass black holes that formed from dying stars, these primordial black holes could range in mass from tiny subatomic specks to millions of times the mass of the Sun. If such objects exist, they should occasionally pass in front of the light from a lensed quasar. When this happens, the gravitational influence of the black hole would briefly magnify the quasar's light in a predictable way, creating a unique kind of flickering pattern. By analyzing these patterns across thousands of lensed quasars, astronomers might be able to detect these ancient remnants from the earliest moments of the universe's existence. But what if lensed quasar echoes could do more than just detect hidden black holes? What if they could provide direct evidence for a fundamental flaw in our understanding of spacetime itself? Some alternative theories of gravity, such as modified Newtonian dynamics, MOND, and emergent gravity, propose that what we currently attribute to dark matter might actually be a breakdown of our standard gravitational laws. If these alternative theories are correct, they should leave specific, detectable imprints on the time delays and magnification patterns of lensed quasar echoes. One of the most intriguing possibilities is that these echoes could reveal whether gravity operates the same way on all scales. General relativity has been tested extensively within our solar system, but its behavior on the largest cosmic scales remains uncertain. Lensed quasars provide a rare opportunity to test Einstein's equations in an environment where the gravitational warping of spacetime is extreme. If the time delays between quasar images deviate even slightly from what general relativity predicts, it could be the first sign that our current understanding of gravity needs revision. Another compelling aspect of lensed quasar echoes is their potential connection to cosmic voids, immense, empty regions of space that contain very few galaxies. These voids, which can span hundreds of millions of light-years, are some of the least understood structures in the universe. Some theories suggest that they might contain exotic forms of dark energy, or even be influenced by quantum fluctuations left over from the Big Bang. If the light from a lensed quasar passes near or through a cosmic void, it could experience unexpected delays or distortions that don't match standard lensing predictions. By carefully studying these anomalies, scientists could probe the large-scale distribution of dark energy and test whether voids are truly empty, or if they contain something even stranger. And then there's the possibility that lensed quasar echoes could help us uncover the true nature of time itself. In standard physics, time is treated as a continuous flow, but some theories suggest that time might be quantized at the smallest scales, much like how matter is made of discrete particles. If time is indeed quantized, then the light from a quasar could experience tiny, random variations as it travels across billions of light-years. By analyzing the time delays in lensed quasar echoes down to the smallest possible fractions of a second, scientists could search for evidence of this granularity in time. If they find it, it would be one of the most profound discoveries in the history of physics, potentially pointing toward a deeper, underlying structure of reality that we have yet to comprehend. The sheer number of ways in which lensed quasars can be used to explore the universe is almost overwhelming. They offer insights into everything from the expansion of space-time to the distribution of hidden matter to the very fabric of reality itself. Every new lensed quasar that is discovered represents another opportunity to test our theories, refine our models, and perhaps even uncover entirely new physics. And with the next generation of telescopes set to revolutionize our ability to observe these phenomena, We are standing on the brink of an era where lensed quasar echoes could become one of the most powerful tools in all of cosmology. The universe has hidden its deepest secrets in these distant, warped images of ancient quasars. But with patience, precision, and the right technology, we may finally be able to decode their messages, and in doing so, unlock the true nature of the cosmos. The potential of lensed quasar echoes extends beyond traditional cosmology and into the very foundations of quantum mechanics and relativity. One of the most ambitious ideas in modern physics is the search for a theory of quantum gravity, a framework that unifies Einstein's general relativity with quantum mechanics. These two pillars of physics work exceptionally well in their respective domains, but they remain fundamentally incompatible when it comes to describing the extreme conditions of black holes and the earliest moments of the universe. Lensed quasar echoes could provide a new testing ground for quantum gravity effects. If space-time itself has a quantum structure, then the light from a quasar traveling billions of light-years through an intervening gravitational lens could pick up subtle, measurable distortions due to quantum fluctuations. Some versions of quantum gravity predict that space-time behaves like a foam, at the smallest scales, with tiny, transient warps that could introduce unpredictable variations in the time delays between quasar images. Detecting these fluctuations would be groundbreaking, offering the first observational proof that space-time is not a continuous fabric but a quantum system with its own discrete structure. Another major mystery that lensed quasar echoes might help unravel is the true nature of cosmic inflation. Inflation is the theory that proposes the universe underwent a rapid expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and explaining why the cosmos appears so uniform on large scales. However, despite strong theoretical and indirect observational support, direct evidence for inflation remains elusive. One of the predictions of inflation is that it should have left behind a specific pattern of fluctuations in the density of the universe. Fluctuations that should, in turn, affect the distribution of gravitational lenses. By analyzing large samples of lensed quasars and their echoes, astronomers could map out the statistical properties of these lenses with unprecedented precision. If these patterns match the predictions of inflation, it would provide some of the strongest evidence yet that the early universe underwent this extraordinary burst of expansion. But if they don't, it could force physicists to reconsider one of the most widely accepted theories in modern cosmology. Beyond fundamental physics, lensed quasar echoes also offer a new way to study the evolution of galaxies and supermassive black holes over cosmic time. Every quasar sits at the heart of a galaxy, powered by a supermassive black hole that consumes vast amounts of surrounding matter. But how these black holes grew to such enormous sizes remains one of the biggest unsolved problems in astrophysics. Because lensed quasars provide multiple images of the same object at slightly different times, they effectively allow astronomers to watch a quasar's activity evolve over scales of weeks, months, or even years. This means scientists can track how the brightness of a quasar changes over time, shedding light on the feeding habits of supermassive black holes and how they interact with their host galaxies. More intriguingly, lensed quasar echoes could help reveal whether some quasars harbor binary supermassive black holes, pairs of enormous black holes orbiting each other after their host galaxies merged. These binary systems are expected to be common in the universe, but direct observational proof remains scarce. If a lensed quasar is actually a binary system, its echoes might show periodic variations in brightness due to the orbital motion of the black holes. Finding such a signal would provide critical evidence for how black holes grow and evolve in the cosmic web. Speaking of the cosmic web, lensed quasar echoes could also help map the vast, interconnected structure of the universe. The large-scale structure of the cosmos is shaped by the distribution of dark matter, forming a complex network of filaments and voids that stretch across billions of light-years. Since gravitational lensing is directly influenced by dark matter, studying lensed quasar echoes provides a unique way to probe this hidden structure. By analyzing how light from quasars is bent and delayed by intervening dark matter, astronomers can create detailed maps of where this invisible substance is concentrated. These maps could reveal whether dark matter behaves exactly as predicted by standard cosmology, or if it exhibits unexpected properties that hint at new physics. Some models suggest that dark matter might interact with itself in subtle ways, affecting how it clusters over time. If lensed quasar echoes show deviations from expected lensing patterns, it could provide the first observational hints of these exotic dark matter interactions. On an even grander scale, lensed quasar echoes might help answer one of the deepest questions in physics. Is our universe truly the only one, or are we part of a vast multiverse? Some theories propose that other universes exist beyond our own, each with different physical laws and fundamental constants. If this is true, then it's possible that traces of these alternate universes could be imprinted on the structure of space-time itself. If lensed quasars reveal subtle distortions in the fabric of space that cannot be explained by known physics, it could hint at interactions between our universe and others. Some models predict that collisions between universes in the early cosmos could leave behind detectable imprints in the form of strange, large-scale anomalies in the way light travels. If lensed quasar echoes show unexplained variations in time delays or magnification, it might be one of the first pieces of observational evidence suggesting that our universe is not alone. The sheer breadth of discoveries that could come from studying lensed quasar echoes is staggering. They offer a window into the deepest workings of gravity, the evolution of black holes and galaxies, the distribution of dark matter, the history of cosmic inflation, and even the possibility of a multiverse. These cosmic beacons, distorted and multiplied by the vast gravitational forces of the universe, hold within them the answers to some of the most profound mysteries ever contemplated by science. And yet, despite their immense importance, lensed quasars remain relatively rare and difficult to study. Finding and analyzing them requires the most advanced telescopes and computing power ever developed. But as new surveys scan the skies with greater precision than ever before, the number of known lensed quasars is expected to increase dramatically. Future observatories, such as the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, will uncover thousands of new lensed quasars, vastly expanding our ability to use them as cosmic probes. With each new discovery, we will refine our understanding of the cosmos, peeling back the layers of mystery that have shrouded our universe for billions of years. Lensed quasar echoes are not just a fascinating curiosity, they are a key to unlocking the deepest truths of existence. They allow us to test the limits of our knowledge, challenge our assumptions, and perhaps even rewrite the very laws of physics themselves. And as we continue to observe, analyze, and interpret the light from these distant beacons, we may find that the echoes they send us across the vast reaches of space are not just messages from the past, but glimpses of the fundamental nature of reality itself. The study of lensed quasar echoes is only just beginning, and the technological advancements of the coming decades promise to revolutionize our ability to analyze these cosmic phenomena. Future space-based observatories and next-generation telescopes will bring unprecedented precision to gravitational lensing studies, potentially revealing new physics hidden in the echoes of these distant beacons. One of the most anticipated developments is the launch of the Nancy Grace Roman Space Telescope, which will survey large portions of the sky with incredible depth and clarity. Unlike previous telescopes, which focused on individual quasars, the Roman Space Telescope will provide a wide-field view that captures thousands of lensed quasars in a single observation. This massive dataset will allow astronomers to study lensed quasar echoes on a scale never before possible, uncovering patterns and anomalies that could hint at unknown forces shaping the universe. At the same time, ground-based observatories like the Vera C. Rubin Observatory will continuously monitor the sky, searching for changes in brightness among known and newly discovered quasars. This observatory's unique Legacy Survey of Space and Time, LSST, will track how quasar images flicker and shift over time, providing a real-time view of lensed quasar echoes. By collecting data over years or even decades, LSST will enable researchers to measure time delays with extreme precision, leading to stronger constraints on the Hubble constant and potential new physics beyond standard cosmology. But even as observational techniques improve, the theoretical side of lensed quasar echoes is evolving just as rapidly. Physicists are using sophisticated machine learning algorithms to model how light interacts with gravitational lenses in complex ways. These AI-driven simulations allow scientists to reconstruct the distribution of dark matter in unprecedented detail, providing deeper insights into its properties and interactions. Some of the most advanced neural networks are even capable of detecting tiny deviations in lensing behavior, subtle clues that could hint at modified gravity theories or the presence of exotic particles. One particularly exciting possibility is that lensed quasar echoes might reveal the existence of primordial black holes, hypothetical black holes that formed in the first moments after the Big Bang. Unlike the supermassive black holes found in galaxies, these primordial black holes could range in size from microscopic to several times the mass of the Sun. If they exist, they might account for some or all of the universe's dark matter, a theory that has long intrigued physicists. Since primordial black holes would act as gravitational lenses, their presence could subtly alter the echoes of lensed quasars. If astronomers detect unexplained distortions in quasar echoes, patterns that don't match what's expected from ordinary galaxies and dark matter halos, it could be evidence that these mysterious objects are lurking in the cosmos. Confirming the existence of primordial black holes would fundamentally reshape our understanding of cosmic evolution, linking the earliest moments of the universe to the dark matter mystery that persists today. Another frontier in lensed quasar echo research is the potential to probe the cosmic neutrino background, the relic neutrinos left over from the Big Bang. Unlike the cosmic microwave background, which consists of ancient photons, the cosmic neutrino background is composed of nearly undetectable neutrinos that permeate space. These elusive particles interact with matter only through the weak nuclear force, making them incredibly difficult to observe directly. However, gravitational lensing might provide an indirect way to detect their effects. If neutrinos have a small but non-zero mass, their presence would slightly alter the way dark matter clumps in the universe, which in turn would affect the time delays of lensed quasar echoes. By analyzing enough quasar systems with extreme precision, astronomers could place constraints on the mass of cosmic neutrinos, helping to complete our picture of the standard model of particle physics. The search for exotic physics doesn't stop there. Some speculative theories suggest that fifth forces, new fundamental forces beyond gravity, electromagnetism, and the nuclear interactions, might subtly influence the propagation of light. If these forces exist, they could introduce tiny but detectable variations in the way light from quasars is bent and delayed. By comparing different lensed quasar systems across the sky, scientists could look for anomalies that might signal the presence of these hidden forces. But while the quest for new physics is thrilling, lensed quasar echoes also have practical applications closer to home. The precise measurement of gravitational time delays can help refine our understanding of Earth's motion through space, improving everything from GPS systems to deep space navigation. Looking further into the future, interferometry-based space missions might allow us to measure quasar echoes with even greater precision. Concepts like the LISA, Laser Interferometer Space Antenna, mission, which aims to detect gravitational waves from orbiting black holes, could potentially be used to study the subtle distortions in quasar echoes with unparalleled accuracy. If these missions succeed, they could provide a direct window into the nature of space-time itself, probing whether Einstein's relativity holds up under extreme conditions. But perhaps the most profound implication of lensed quasar echoes is their connection to the ultimate fate of the universe. If dark energy, the mysterious force driving the acceleration of cosmic expansion, changes over time, it could have dramatic consequences for the universe's long-term evolution. Some models predict that dark energy might strengthen, leading to a Big Rip scenario where galaxies, stars, and even atoms are torn apart. Others suggest that dark energy might weaken, causing the universe to eventually collapse in a big crunch. Lensed quasar echoes offer one of the best ways to track how dark energy evolves by measuring how the universe expands at different points in cosmic history. If variations in time delays show unexpected shifts, it could hint that dark energy is not a constant force but something more dynamic. Such a discovery would completely reshape our understanding of the cosmos and its ultimate destiny. The implications of studying lensed quasar echoes extend far beyond astronomy. They touch on the deepest questions about reality itself. Are the laws of physics truly constant across time and space? Do hidden dimensions influence the way gravity behaves on cosmic scales? Is our universe connected to others in ways we have yet to comprehend? each new observation brings us closer to answers. The echoes of quasars, distorted and delayed by gravity, are like messages from the distant past, revealing secrets that have been locked away for billions of years. As our technology improves and our theories evolve, these cosmic signals may one day provide the key to understanding the very fabric of existence. And so, we continue to look deeper, to measure more precisely, and to ask ever more profound questions. The universe speaks in the language of light, and through lensed quasar echoes, we are finally learning to listen. Lensed quasar echoes are more than just a cosmic curiosity. They are a direct probe into some of the most profound mysteries of the universe. As we refine our ability to analyze these echoes, we move closer to unraveling the nature of dark matter, dark energy, and the very structure of space-time itself. But what makes these echoes so special is that they allow us to see the universe not as a static, unchanging entity, but as a dynamic, evolving landscape where gravity bends light, warps time, and reveals hidden truths. One of the most promising developments in this field is the detection of microlensing events within lensed quasars. While a typical strong gravitational lensing event creates multiple large-scale images of a quasar, microlensing occurs when individual stars or compact objects within the foreground galaxy cause tiny, unpredictable variations in brightness. These microlensing events can be incredibly useful for studying the distribution of dark matter on small scales. If dark matter consists of massive but unseen objects, such as primordial black holes, then their gravitational influence should create distinctive patterns in lensed quasar echoes. On the other hand, if dark matter is composed of weakly interacting particles that form smooth halos, the microlensing signatures will be different. By analyzing thousands of quasar microlensing events, astronomers can test competing theories of dark matter and potentially solve one of the greatest mysteries in physics. But beyond dark matter, microlensing also provides a way to measure the internal structure of quasars themselves. Even though quasars are among the brightest objects in the universe, they are so far away that their detailed structures remain elusive. Microlensing acts as a natural telescope, magnifying different parts of the quasar's accretion disk at different times. By studying how the light changes, astronomers can reconstruct the size, temperature, and composition of the disk, something that would otherwise be impossible. This has led to some surprising discoveries. Observations of lensed quasar echoes suggest that the regions closest to the quasar's supermassive black hole emit light in unexpected ways. Instead of a simple, smooth accretion disk, some quasars appear to have irregular, clumpy structures that defy standard models. Could this be evidence of exotic physics near black holes? Are we seeing the effects of magnetic fields, turbulence, or even new, undiscovered quantum effects playing out on cosmic scales? These questions take us even deeper into the unknown. Some physicists speculate that lensed quasar echoes could provide a testing ground for quantum gravity, a field of study that seeks to merge general relativity with quantum mechanics. According to certain theories, space-time at the smallest scales is not continuous but instead quantized, meaning that light traveling through different paths around a gravitational lens might be subtly affected by these quantum effects. If such deviations are ever detected, it would provide the first real evidence of quantum gravity in action. Another emerging idea is that lensed quasar echoes might be influenced by the existence of extra dimensions. In string theory and other high-dimensional models, gravity is thought to leak into hidden dimensions beyond the familiar 3 of space and 1 of time. If true, this could cause small but measurable distortions in the way light from quasars is lensed. Detecting such distortions would be revolutionary, providing evidence that the universe is far more complex than it appears. But for now, the search continues. As new telescopes come online and our data analysis techniques improve, we may soon unlock deeper secrets hidden in the echoes of lensed quasars. What we learn could reshape our understanding of the cosmos, bridging the gap between the known and the unknown. Each observation, each measurement, and each new discovery brings us one step closer to answering the biggest questions about the nature of reality itself. Lensed quasar echoes continue to push the boundaries of our understanding of the universe. They act as natural laboratories where we can test our most fundamental theories about gravity, space-time, and even the very fabric of reality. But to truly appreciate their significance, we need to take a step back and explore how these echoes can serve as a cosmic time machine, offering us glimpses into the past with unprecedented clarity. Because light from a quasar takes different paths around a gravitational lens, each path has a different length. This means that when a quasar's brightness changes, the changes appear in different images at different times. This is what we call a quasar echo. These time delays are not just fascinating observational effects, they allow astronomers to measure the expansion rate of the universe, also known as the Hubble constant. The Hubble constant is one of the most important numbers in cosmology, as it determines the age, size, and fate of the universe. However, there's a major problem. Different methods of measuring it give different results. This is known as the Hubble tension, and it has led scientists to question whether we truly understand the universe's expansion. Lensed quasar echoes provide a new way to measure the Hubble constant by timing the delays between images and comparing them to precise models of gravitational lensing. If these measurements confirm one of the existing values, we might resolve the tension. But if they suggest something completely different, we could be looking at new physics beyond our current models. This idea becomes even more exciting when we consider the role of dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, and its nature remains one of the biggest unanswered questions in physics. By studying lensed quasar echoes over long periods, astronomers can track how the expansion rate has changed over billions of years. If dark energy behaves differently at different times, it could mean that our understanding of the fundamental forces of nature is incomplete. Some theories suggest that dark energy might not be a constant force, but rather a dynamic entity that evolves over time. Lensed quasars could provide crucial evidence to determine whether this is the case. But perhaps the most mind-bending possibility is that lensed quasar echoes could help us detect violations of Einstein's theory of general relativity. General relativity has been incredibly successful in explaining how gravity works on large scales, but we know that it is incomplete because it does not incorporate quantum mechanics. Some alternative theories predict that gravity might behave slightly differently in extreme environments, and one way to test this is by looking for unexpected shifts in lensed quasar echoes. If light from a quasar is bent in ways that do not match Einstein's predictions, it could point to a new, deeper theory of gravity waiting to be discovered. At the same time, lensed quasar echoes could also serve as probes for some of the strangest and most exotic objects in the universe. One possibility is that some of the foreground galaxies acting as gravitational lenses might contain wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe. If a wormhole were present in a lensing galaxy, it might create unusual distortions in the way light from a quasar is bent, producing anomalies in the time delays between images. While this is still speculative, the fact that we now have the technology to even search for such effects is a testament to how far we've come in our understanding of the cosmos. Another possibility is that lensed quasar echoes could reveal the presence of cosmic strings, theoretical one-dimensional defects in spacetime that might have formed in the early universe. These cosmic strings could act as gravitational lenses themselves, creating unusual patterns in quasar echoes that would be unmistakable. Detecting a cosmic string would be groundbreaking, providing direct evidence of processes that took place just fractions of a second after the Big Bang. As our telescopes become more advanced, our ability to study lensed quasars will only improve. The upcoming Vera C. Rubin Observatory is expected to detect thousands of new lensed quasars, dramatically increasing the number of systems available for study. With more data, we can refine our models, test new theories, and perhaps uncover hidden physics that has eluded us until now. The echoes of lensed quasars are more than just delays in light. They are whispers from the depths of the cosmos, revealing secrets that challenge everything we think we know. Whether they confirm our current theories or force us to rewrite the laws of physics, one thing is certain: they are among the most powerful tools we have for unlocking the mysteries of the universe. Lensed quasar echoes are more than just an observational phenomenon. They serve as a direct test of the most fundamental principles governing the universe. Every time a quasar's light bends around a massive galaxy and reaches us through multiple pathways, it carries encoded information about spacetime itself. The delays between the multiple images allow us to measure cosmic distances with extreme precision, helping us refine our understanding of the large-scale structure of the universe. But what if these echoes reveal something unexpected, something that forces us to question our most basic assumptions about reality? One of the most fascinating possibilities is that lensed quasar echoes could provide evidence for hidden structures in the universe that we cannot otherwise detect. While we traditionally think of space as mostly empty, modern physics suggests that it might be filled with unseen filaments of dark matter, exotic particles, and possibly even extra dimensions. When light from a distant quasar travels through this cosmic web, it might be subtly altered in ways that we can measure by analyzing lensing anomalies. If we ever detect deviations that cannot be explained by conventional physics, we might be looking at the first observational proof of physics beyond the standard model. This is where one of the most controversial ideas in modern physics comes into play: the possibility that lensed quasar echoes could provide indirect evidence for quantum gravity effects. According to some theories, space-time itself is not smooth but rather has a discrete, granular structure at the smallest scales. This means that light traveling through the cosmos could be subtly distorted by quantum fluctuations in space-time, causing tiny shifts in the time delays between lensed quasar images. If these shifts ever deviate from what general relativity predicts, we could be looking at direct evidence of a quantum structure to space-time, one of the holy grails of modern physics. And then there's the possibility that lensed quasar echoes could reveal the presence of exotic, unseen objects lurking in the universe. Some astronomers have speculated that massive, ultra-compact objects, possibly primordial black holes or even hypothetical objects like gravastars or boson stars, could exist in the foreground galaxies that act as gravitational lenses. If such objects are present, they could create subtle but measurable distortions in the lensing patterns of quasar echoes. Detecting such an effect would not only prove that these exotic objects exist but could also provide insights into the nature of dark matter itself. Perhaps even more intriguing is the idea that lensed quasar echoes could be used to probe the very fabric of time. The fact that different images of a quasar arrive at different times means that we are effectively seeing the same event play out at multiple moments in history. Some physicists have suggested that, under certain extreme conditions, we might be able to use these time delays to test whether time itself is truly continuous or whether it might exhibit small-scale quantum fluctuations. If time is not as smooth and uniform as we assume, it would revolutionize our understanding of reality in ways we can barely begin to imagine. But even within the framework of conventional physics, lensed quasar echoes have the potential to rewrite our understanding of the structure and evolution of galaxies. Every time a quasar's light is bent by a foreground galaxy, it provides us with an opportunity to map the distribution of both visible and dark matter within that galaxy. This has led to some surprising discoveries, such as the fact that many galaxies appear to have much more irregular and clumpy distributions of dark matter than expected. If this turns out to be a universal pattern, it could force us to reconsider our models of galaxy formation and the role that dark matter plays in shaping the universe. Looking to the future, upcoming telescopes like the Nancy Grace Roman Space Telescope and the James Webb Space Telescope will allow us to study lensed quasar echoes with unprecedented precision. With these instruments, we will be able to detect even smaller variations in time delays, measure lensing distortions with greater accuracy, and potentially uncover new physics hidden in the light of distant quasars. The echoes of lensed quasars are not just reflections of the past, they are signals from the edge of knowledge, pointing us toward the unknown. As we continue to refine our measurements, analyze new data, and push the boundaries of what we can observe, we may find ourselves on the verge of discoveries that will reshape our understanding of the cosmos forever. Lensed quasar echoes hold the key to some of the biggest unanswered questions in astrophysics. They are more than just distortions in light. They are a gateway to understanding the hidden forces shaping the universe. The more we study them, the more we realize they can be used as precision tools for measuring cosmic parameters, testing fundamental physics, and uncovering secrets that would otherwise remain buried in the depths of space. One of the most compelling ways in which lensed quasar echoes push the boundaries of our knowledge is through precision cosmology. The delays in the arrival of quasar light from different paths allow us to construct an incredibly detailed map of space-time curvature on cosmological scales. This enables us to measure distances across the universe with an accuracy that rivals, or even surpasses, traditional methods like supernova measurements or baryon acoustic oscillations. By combining quasar echo data with other cosmological observations, scientists can refine their estimates of key parameters like the Hubble constant, the density of dark matter, and the influence of dark energy. But the real intrigue begins when we realize that lensed quasar echoes might also provide clues about the true nature of dark matter. Dark matter remains one of the most perplexing mysteries in physics. We know it exists because of its gravitational effects, but we have never directly detected it. However, gravitational lensing offers a unique way to see dark matter, even though it is invisible to traditional telescopes. If dark matter is composed of exotic particles that behave differently from what our current models predict, its distribution could cause small distortions in the time delays of quasar echoes. By carefully analyzing these distortions, we might be able to determine whether dark matter is truly cold and non-interacting or whether it exhibits unexpected quantum effects. There is also the possibility that some of the foreground galaxies bending the quasar's light contain substructures of dark matter that have never been observed before. In some models, dark matter might not be smoothly distributed but could instead exist in the form of small, dense clumps or even microscopic black holes. If these structures are present, they could create tiny but detectable changes in the arrival times of lensed quasar images. Such a discovery would be groundbreaking, as it would provide direct evidence of how dark matter is arranged on the smallest scales. But the significance of lensed quasar echoes doesn't stop at dark matter. They also offer a unique way to probe the existence of exotic space-time defects, such as cosmic strings. Cosmic strings are hypothetical one-dimensional cracks in space-time that may have formed in the early universe due to symmetry-breaking transitions. If a cosmic string were to pass between us and a lensed quasar, it could warp space-time in an unusual way, creating an unexpected shift in the arrival times of quasar echoes. The detection of a cosmic string would be one of the most profound discoveries in modern physics, as it would provide direct evidence for physics beyond the standard model and possibly even insights into quantum gravity. This brings us to another mind-blowing implication. Lensed quasar echoes could help us detect modifications to general relativity itself. Einstein's theory of general relativity has withstood every test thrown at it so far, but we know it is incomplete because it does not incorporate quantum mechanics. Some alternative theories predict that gravity might behave slightly differently on cosmic scales, leading to tiny deviations in the way light is bent by massive objects. By comparing the observed time delays in quasar echoes with the predictions of general relativity, we could potentially spot subtle effects that hint at new physics, perhaps even pointing toward a deeper, quantum theory of gravity. Even more astonishing is the possibility that lensed quasar echoes could reveal hidden aspects of the structure of time itself. Some speculative theories suggest that time is not a continuous flow but rather a discrete sequence of tiny quantum events. If this is true, we might be able to detect anomalies in the time delays between quasar echoes that do not match classical expectations. If confirmed, such a discovery would shake the foundations of physics, forcing us to rethink the very nature of reality. And then there's the idea that quasar echoes might provide evidence for wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe. If a wormhole existed within a gravitational lensing system, it could create unusual distortions in the light paths of a quasar, potentially producing lensing effects that differ from those predicted by standard general relativity. While no direct evidence for wormholes has been found, the possibility that they could leave a signature in lensed quasar echoes remains an exciting avenue for research. With the next generation of telescopes set to revolutionize our ability to detect and analyze these echoes, we are entering an era where the universe may begin revealing secrets we never even imagined. The Vera C. Rubin Observatory, for instance, is expected to discover thousands of new lensed quasars, allowing for statistical analyses on an unprecedented scale. Meanwhile, instruments like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will enable us to observe these systems in even greater detail, capturing the finest distortions in light as it bends around massive objects. The echoes of lensed quasars are more than just fascinating cosmic phenomena. They are signals from the deep past, whispering secrets about the universe's most hidden forces. Whether they confirm our current models or force us to rewrite the laws of physics, one thing is certain: they will continue to challenge and expand our understanding of the cosmos for decades to come. Lensed quasar echoes are not just a tool for studying cosmology and dark matter. They also open a window into the inner workings of black holes and active galactic nuclei, AGN. Quasars are powered by supermassive black holes at the centers of galaxies, consuming enormous amounts of matter and emitting incredible energy. The way light from these quasars is delayed, distorted, and split into multiple images by gravitational lenses allows astronomers to peer into the structure of the accretion disks surrounding these black holes. Accretion disks are the swirling rings of gas and dust that feed supermassive black holes. These disks are among the most extreme environments in the universe, where gravity, magnetism, and radiation interact in ways that are still not fully understood. The light from the inner regions of a quasar's accretion disk undergoes microlensing effects when passing through the gravitational fields of individual stars in the foreground galaxy. This microlensing creates tiny variations in the brightness of different lensed images of the quasar, which scientists can analyze to determine the size, structure, and even temperature distribution of the accretion disk. By studying these microlensing effects over time, researchers can also track changes in the accretion disk itself, revealing details about how black holes consume matter and how they generate powerful relativistic jets. These jets, which can extend for millions of light years, are responsible for shaping galaxies and redistributing matter across the cosmos. The physics behind them remains one of the biggest mysteries in astrophysics, and lensed quasar echoes may hold the key to solving it. Even more intriguing is the potential for using lensed quasar echoes to test the no-hair theorem of black holes. According to Einstein's general relativity, black holes are fully described by just three properties: mass, spin, and electric charge, meaning they have no hair or additional features. However, some alternative theories of gravity suggest that black holes might possess additional properties or exotic structures around them. If such deviations exist, they could subtly affect the way light from a quasar's accretion disk is lensed, creating unexpected variations in the arrival times of quasar echoes. Detecting such variations could be one of the first signs that black holes are more complex than we currently believe. But the mysteries don't stop there. Lensed quasar echoes might also provide clues about the expansion history of the universe. One of the greatest challenges in modern cosmology is understanding the true rate at which the universe is expanding. Different measurement techniques, such as using supernovae, cosmic microwave background radiation, and baryon acoustic oscillations, have led to slightly different values for the Hubble constant, the parameter that describes cosmic expansion. This discrepancy, known as the Hubble tension, suggests that there might be unknown physics at play. Lensed quasars offer an independent method of measuring the Hubble constant. By carefully timing the delays between different quasar echoes and comparing them with models of gravitational lensing, astronomers can determine distances across the universe with incredible precision. If the values obtained from lensed quasar echoes match one of the current measurements of the Hubble constant, it could help resolve the ongoing tension. But if they point to a completely different value, it might mean that our understanding of cosmic expansion needs to be revised, potentially hinting at new physics beyond our current models. One particularly wild idea that has been proposed is that lensed quasar echoes could reveal evidence for a cyclic universe, where the cosmos undergoes repeated cycles of expansion and contraction. Some alternative cosmological theories suggest that instead of originating from a single Big Bang, the universe might have expanded and collapsed multiple times over cosmic history, with each cycle leaving behind subtle imprints in the structure of space-time. If such cyclic behavior affects the distribution of massive lensing galaxies, it could create small but detectable anomalies in the time delays of lensed quasars. While still highly speculative, this idea shows just how much potential these cosmic echoes have for reshaping our understanding of the universe. Another exciting frontier in lensed quasar research is the possibility of detecting gravitational waves from the early universe. When massive objects like black holes merge, they send ripples through space-time known as gravitational waves. So far, we have only detected high-frequency gravitational waves from relatively recent events, such as black hole and neutron star mergers. But some theories predict that the early universe may have been filled with low-frequency gravitational waves left over from the Big Bang or cosmic inflation. If these ancient gravitational waves exist, they could slightly alter the way light from lensed quasars propagates through space, creating small variations in their time delays. By studying these variations, astronomers might be able to detect some of the oldest gravitational waves in existence, offering a direct glimpse into the conditions of the universe shortly after its birth. This would be an unprecedented breakthrough, potentially providing the first direct evidence for inflation, the rapid expansion of the universe in its earliest moments. The study of lensed quasar echoes is only just beginning. As technology advances and new telescopes come online, we will be able to detect fainter, more distant quasars and analyze their echoes in even greater detail. Future missions such as the Square Kilometre Array, SKA, and the Extremely Large Telescope, ELT, will allow us to probe deeper into the cosmos than ever before, uncovering more gravitationally lensed quasars and refining our measurements of time delays with unprecedented accuracy. The implications of these discoveries are staggering. Are we living in a universe that behaves exactly as we expect, or are there hidden forces at play that we have yet to uncover? Could lensed quasar echoes reveal unexpected properties of space-time, hidden structures of dark matter, or even the fingerprints of unknown dimensions? The more we study them, the more they seem to hold the answers to some of the most profound questions in physics. And perhaps the most mind-bending possibility of all is that lensed quasar echoes could eventually lead us to a unified theory of physics, one that bridges the gap between quantum mechanics and general relativity. These two pillars of modern physics work beautifully in their own domains, but they are fundamentally incompatible with each other. The behavior of light around a gravitational lens might contain subtle clues about how quantum effects influence the warping of spacetime, providing hints that could one day lead us to the elusive theory of quantum gravity. What began as a simple observation, the splitting of a quasar's light into multiple images, has now evolved into one of the most powerful tools in astrophysics. With every new discovery, lensed quasar echoes continue to surprise us, challenge us, and push the boundaries of what we think we know about the universe. The more we listen to their whispers, the closer we get to unraveling the deepest mysteries of reality itself. Lensed quasar echoes are more than just a fascinating astrophysical phenomenon. They are a cosmic time machine, a tool that lets us look back across billions of years and observe how the universe has evolved. But as we continue to refine our techniques and analyze more quasar echoes, we are beginning to realize that they may hold even deeper secrets. Secrets that could fundamentally change how we understand the structure of the cosmos itself. One of the biggest mysteries that lensed quasar echoes could help solve is the nature of dark matter. Scientists have known for decades that the majority of the universe's mass does not come from ordinary matter. Stars, planets, gas clouds, and even black holes make up only a small fraction of the total mass of the cosmos. The rest appears to be something completely different, an invisible, non-luminous form of matter that interacts with gravity but does not emit or absorb light. Dark matter's presence is inferred from its gravitational influence on galaxies and clusters of galaxies. But despite years of searching, no one has been able to detect a dark matter particle directly. This has led to countless theories about what dark matter could actually be. Some suggest it is made of unknown subatomic particles, while others propose that it might be linked to new physics beyond our current understanding of the universe. Lensed quasars provide an incredible way to map the distribution of dark matter in unprecedented detail. Because gravitational lensing is sensitive to all forms of mass, including dark matter, the way light from a quasar is bent and split into multiple images can tell us a great deal about the mass distribution of the foreground lensing galaxy. By analyzing small distortions in the images of lensed quasars, astronomers can detect clumps of dark matter that would otherwise be invisible. This technique has already led to some unexpected discoveries. In several cases, researchers have found tiny, isolated clumps of dark matter floating in space without any visible stars or galaxies. This suggests that dark matter may form structures on much smaller scales than previously thought, challenging current models of how it behaves. Some of these dark matter clumps appear to be more compact and dense than expected, leading to speculation that they might contain primordial black holes, tiny black holes that formed in the early universe and could be a candidate for dark matter itself. But there is an even bigger mystery lurking in the background, one that could completely redefine physics as we know it. Some researchers believe that dark matter might not be a substance at all, but rather an illusion created by a deeper, hidden property of space-time. This idea, known as modified gravity, suggests that our current understanding of gravity may be incomplete. Instead of being caused by a mysterious invisible substance, the strange effects attributed to dark matter might arise from hidden interactions between space-time and quantum fields. Lens quasar echoes could provide a crucial test for this idea. If modified gravity is correct, then the bending of light around massive objects should behave slightly differently than predicted by Einstein's theory of general relativity. By carefully analyzing the time delays between quasar echoes, scientists can check for tiny deviations in the way light propagates through space-time. If any unexpected anomalies are found, they could be the first real evidence that gravity itself behaves differently on cosmic scales. Another mind-blowing possibility is that lens quasar echoes could reveal evidence for extra dimensions. Some theories of physics suggest that the universe may have more than the 4 dimensions we experience, 3 of space and 1 of time. These extra dimensions, if they exist, could be curled up at incredibly small scales, making them invisible to direct observation. However, they might still affect the way light travels through space. If extra dimensions exist, they could cause subtle distortions in the paths of gravitationally lensed quasars, leading to time delays that don't match what standard physics predicts. Some researchers have even proposed that if these extra dimensions are large enough, they could create ghost images of lensed quasars, faint, distorted echoes that appear in unexpected locations. Detecting such a phenomenon would be a groundbreaking discovery, proving that our universe is far stranger than we ever imagined. And then there's the biggest mystery of all, the nature of time itself. Lensed quasar echoes are, at their core, a study of how light and time interact on cosmic scales. But what if time is not as straightforward as we think? Some physicists have suggested that time might not be a smooth, continuous flow, but rather a series of discrete, quantum-like events. If this is true, then time itself might behave in strange and unpredictable ways, especially near massive objects like black holes and cosmic filaments of dark matter. One radical idea proposes that time might have a grainy structure, where small fluctuations on the quantum scale can affect the way light travels. If such an effect exists, it could slightly alter the arrival times of quasar echoes, creating patterns that don't match what classical physics predicts. Detecting such a pattern would be one of the greatest discoveries in the history of science, potentially leading to a complete rethinking of what time really is. But we are only scratching the surface. As telescopes continue to improve and new data from missions like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope become available, the study of lensed quasar echoes is about to enter a new golden age. With each new discovery, we are learning more about the hidden forces that shape the universe, and we are inching closer to solving some of the deepest puzzles in physics. The echoes of distant quasars are whispering secrets across time and space, carrying messages from the dawn of the cosmos. The more we listen, the more we realize that the universe is far more mysterious than we ever imagined. What other surprises are waiting to be uncovered? What other cosmic echoes are still out there, waiting to be heard? The more we analyze lensed quasar echoes, the more we realize that they are not just a convenient method for measuring cosmic distances or mapping dark matter. They are a direct window into the hidden fabric of reality itself. Each time a quasar's light is bent, split, and echoed across vast stretches of the universe, it carries with it clues that could ultimately lead us to answers about the deepest questions in physics. One of the strangest implications of lensed quasar echoes is their potential connection to the holographic principle, the idea that our three-dimensional universe might actually be a kind of projection from a two-dimensional surface. This theory, originally inspired by black hole physics, suggests that the fundamental laws of the universe might not operate the way we think they do. Instead of space being a vast, continuous expanse, it might be a kind of emergent illusion created from deeper quantum information stored at the boundaries of reality. If this idea is correct, it would mean that everything we experience, including time itself, could be the result of encoded information on a distant, higher dimensional surface. But how would we ever test such a mind-bending idea? Lens quasar echoes might be one of the best tools we have. If the holographic principle is true, then the way light propagates across the cosmos should contain subtle, telltale patterns, small deviations in the expected time delays of quasar echoes that hint at an underlying, encoded structure to reality. Scientists have already begun searching for such effects. Some physicists suspect that if the universe is holographic, then there should be tiny, quantum-level fluctuations in the fabric of space-time itself, and these fluctuations should leave faint imprints on the way light from quasars reaches us. So far, the evidence is inconclusive, but the idea remains tantalizing. If lens quasar echoes ever reveal unexpected, unexplained irregularities, it might be the first real proof that reality is not what it seems. But there is another mystery that lens quasar echoes might help solve, and it's one of the biggest puzzles in modern physics. Why does time only flow in one direction? In everyday life, time moves forward. We remember the past, but we cannot remember the future. We experience cause leading to effect, never the other way around. This is known as the arrow of time, and it is one of the most fundamental aspects of our existence. But from a purely physical perspective, time doesn't have to behave this way. The fundamental laws of physics, as written in Einstein's equations and the principles of quantum mechanics, do not require time to flow in only one direction. So why does it? One idea is that the arrow of time is linked to entropy, the tendency of systems to move from order to disorder. The universe started in a low entropy, highly ordered state, and over time, it has become more chaotic. This increase in entropy gives time its directionality. But what if this explanation is incomplete? What if the structure of time itself has hidden complexities we have not yet discovered? Lens quasar echoes might provide a way to test this. Because these echoes act like a cosmic clock, giving us multiple views of the same quasar at different points in time, they allow scientists to study whether time behaves differently in different regions of space. If the arrow of time is purely an emergent property of entropy, then quasar echoes should behave exactly as expected. But if there is something deeper at play, if time itself has an intrinsic structure that we do not yet understand, then we might see subtle distortions in the time delays between quasar echoes that do not fit any known physical model. There's even a possibility that lens quasar echoes could reveal evidence for time loops, regions of space where time folds back on itself in strange and unexpected ways. Some theoretical physicists propose that certain conditions in the universe, such as extreme warping of space-time near massive objects, could create closed time-like curves, essentially shortcuts through time. If such regions exist, then light from distant quasars could pass through them, creating anomalous time delays that appear to defy causality. Imagine detecting a lens quasar echo where the older image of the quasar appears to be responding to something that hasn't happened yet. Such a discovery would be shocking, evidence that time is not as linear as we think it is. While this idea remains speculative, it is exactly the kind of thing that astronomers are searching for as they analyze increasingly detailed quasar data. And then there's the question of whether quasar echoes could reveal hints of entirely new physics, something beyond our current understanding of the universe. Many scientists believe that Einstein's theory of general relativity, while extremely successful, is not the final word on gravity. There are still unexplained mysteries, such as the nature of dark energy, the force that is causing the universe to expand at an accelerating rate. If dark energy is not simply a cosmological constant, but rather the result of a deeper, hidden structure in space-time, then it could subtly affect the way light travels across the cosmos. Lens quasar echoes might hold the key to detecting this effect. By carefully analyzing the way time delays behave in different regions of the universe, scientists could look for patterns that hint at a previously unknown force at work, something beyond dark matter and dark energy, something completely new. There is a growing suspicion among physicists that the universe may be far stranger and more complex than we ever imagined. The standard model of physics explains a great deal, but it fails to unify gravity with quantum mechanics. Some researchers believe that the key to solving this puzzle lies in hidden dimensions, exotic particles, or entirely new laws of physics. And lensed quasar echoes, by providing a natural, cosmic-scale laboratory for testing these ideas, might be the first place we find direct evidence of these new physical principles. Imagine if, in the coming years, astronomers discover something so unexpected, so unexplainable in quasar echoes that it forces a complete rethinking of physics. What if time itself is not as stable as we think? What if hidden dimensions subtly alter the path of light? What if the echoes of quasars reveal fluctuations in the very fabric of reality, evidence that space-time itself is not smooth, but rather a shifting, dynamic entity shaped by forces we have yet to comprehend? Every time we look deeper into the cosmos, we find surprises. And lensed quasar echoes, with their ability to stretch time, bend space, and reveal the hidden structure of the universe, are one of the most exciting frontiers in modern astrophysics. The universe is speaking to us in light that has traveled for billions of years, shaped by gravity, warped by unseen forces, and echoed across the vastness of space. It is up to us to listen, to decode the messages hidden in these cosmic reflections and uncover the ultimate secrets of reality itself. Lensed quasar echoes are not just a fascinating quirk of gravitational lensing. They are one of the most powerful tools we have for probing the nature of time, space, and the fundamental laws of physics. Every time light from a quasar takes multiple paths through the warped fabric of space, it offers us a rare opportunity, a chance to see how the universe really works on the grandest of scales. But what if these echoes don't just tell us about the past? What if, in some strange way, they hint at the future? This idea might sound impossible, but in physics, time is not as straightforward as we perceive it. We experience time as a one-way street, always moving forward, but that's just because we live at a scale where entropy dominates. If we zoom out and look at the universe from a purely relativistic perspective, the future and the past exist simultaneously. They are just different locations in a four-dimensional space-time continuum. And if time is not as rigid as we assume, then quasar echoes might contain subtle hints that challenge our understanding of causality itself. Consider this. When light from a quasar is bent around a massive galaxy, we see multiple images of the same quasar, but each one comes from a slightly different time due to differences in the light's travel distance. What if, buried within those echoes, there are signals that seem to anticipate future events? This isn't mere speculation. Scientists have already observed bizarre anomalies in gravitational lensing data that defy easy explanation. For example, in some cases, quasar echoes do not arrive exactly when expected based on our best models of general relativity and gravitational lensing. There have been instances where astronomers predicted the appearance of a new lensed image, only for it to show up too soon or too late. This suggests that there could be unknown forces at play, something beyond our current understanding of space-time. One possibility is that these unexpected time delays are due to exotic forms of dark matter, creating tiny distortions in space-time that subtly alter the paths of light. But another, more radical possibility is that the universe itself has hidden, built-in feedback loops, where time does not always behave in the linear, predictable way we assume. Imagine if some regions of the universe allow for small-scale violations of causality, where the flow of time can momentarily fold back on itself. This would mean that under the right conditions, we might see lensed quasar echoes where one image appears to be responding to information that hasn't even arrived yet. It would be as if the universe itself was whispering secrets about what's to come, encoded in the echoes of distant quasars. Could this be a glimpse into a deeper reality, one where time is not fixed, but fluid? Could lensed quasar echoes provide the first observational evidence of hidden structures in time itself? If so, then these cosmic reflections might not just be windows into the past. They might be clues to the future of physics. But the implications go even further. If quasar echoes can reveal hidden distortions in time, then they might also provide insight into one of the greatest mysteries in theoretical physics: the nature of quantum gravity. Right now, We have two incredibly successful but fundamentally incompatible theories: general relativity, which describes gravity on large scales, and quantum mechanics, which governs the subatomic world. For decades, physicists have struggled to unify them into a single, all-encompassing theory of quantum gravity. Some of the leading candidates for this grand theory, such as string theory and loop quantum gravity, predict that space-time itself is not smooth, but made up of tiny, discrete units at the smallest possible scales. If this is true, then light passing through deep space should occasionally interact with these hidden quantum structures, creating subtle distortions in its path that accumulate over billions of years. And guess what? Lensed quasar echoes provide the perfect natural experiment to test this. By measuring quasar echoes at unprecedented precision, astronomers could look for tiny deviations from what general relativity predicts, minute shifts in the time delays that hint at an underlying, quantum nature of space-time. If such an effect is ever detected, it would be one of the most groundbreaking discoveries in the history of physics. Direct observational proof that space and time are not continuous, but composed of a deeper, more fundamental fabric. But here's where things get even stranger. If quasar echoes interact with this quantum fabric, then it raises a chilling question: what if space-time itself is not fundamental, but emergent? There's a growing belief among physicists that space and time might not be fundamental aspects of reality, but rather high-level phenomena that emerge from deeper quantum processes. This idea suggests that just as temperature emerges from the motion of particles, or just as consciousness emerges from the interactions of neurons, space-time itself might be an illusion created by deeper quantum entanglements at a fundamental level of reality. If this is true, then lensed quasar echoes might allow us to detect ripples in this hidden, quantum structure of the universe. We could be looking at echoes not just across space, but across layers of reality itself, hints that the three-dimensional universe we experience is just a shadow of something far more complex. Could this be the ultimate secret hidden within quasar echoes? Could these cosmic reflections be the first direct evidence that our reality is fundamentally quantum, and that time itself is just an emergent property of deeper physics? If so, then every lensed quasar we observe is more than just a distant beacon of light. It is a message from the fundamental structure of the universe itself, waiting to be decoded. The more we study these echoes, the more we realize that they are not just a curiosity of gravitational lensing. They might be the key to unraveling the deepest mysteries of space, time, and the very nature of reality. And if that's true, then the question we must ask ourselves is this: what else is the universe trying to tell us? Lensed quasar echoes are not just a quirk of gravitational lensing. They are a natural time machine that allows us to see cosmic events unfold in multiple ways, offering a unique way to test the very fabric of reality. The deeper we look into these echoes, the more we realize that they might not only be revealing the nature of space-time but also exposing hidden forces that could redefine our understanding of the universe itself. One of the strangest aspects of lensed quasar echoes is that they sometimes don't behave as expected. While the standard model of general relativity predicts precise time delays between multiple images of a quasar, observations have revealed unexplained discrepancies, echoes that arrive too early, too late, or with unexpected shifts in brightness. Could this be evidence of hidden dimensions? Could it hint at a deeper structure within the universe that we have yet to fully grasp? To understand why this is such a big deal, let's break down what's happening. When light from a quasar passes by a massive galaxy, it gets bent and split into multiple paths. Each of these paths takes a different amount of time to reach us, creating multiple images of the quasar that flicker at different moments in cosmic history. If general relativity is perfectly correct, these time delays should be 100% predictable based on the mass distribution of the lensing galaxy. But that's not always what we see. In some cases, the quasar echoes arrive out of sync, as if some unknown force is distorting the travel time of light in a way that standard physics can't explain. This has led some researchers to consider radical possibilities, such as the existence of hidden fifth forces, exotic forms of dark matter, or even microscopic wormholes that subtly alter the path of photons. One possibility is that dark matter is not as smooth as we think. In most models, dark matter is treated as a vast, invisible cloud that surrounds galaxies, warping spacetime with its immense but unseen gravity. But what if dark matter is actually clumpy, chaotic, or even capable of interacting with itself in complex ways? If that were the case, then light from lensed quasars might be passing through small, unexpected gravitational distortions, tiny ripples in spacetime that shift the timing of quasar echoes in unpredictable ways. Another, even more mind-bending idea is that quasar echoes could be revealing hidden connections between different points in spacetime. If microscopic wormholes exist, they could create tiny shortcuts through the universe, allowing some photons to take unexpected detours that slightly alter the arrival times of lensed images. This would mean that quasar echoes are not just revealing gravitational lensing effects, but potentially hinting at a deeper cosmic network of interconnected spacetime pathways. Could this be a glimpse into a hidden layer of reality? Could these echoes be the first observable sign of extra dimensions, regions of space beyond our three-dimensional experience that subtly influence the way light moves through the cosmos? Some theories, such as string theory, predict that extra dimensions could be compactified and hidden from view, but they might still affect gravitational interactions in tiny, nearly undetectable ways. If lensed quasar echoes are behaving strangely, they might be the best evidence yet that extra dimensions are more than just a theoretical curiosity. And what if these anomalies aren't just revealing spatial distortions, but temporal distortions as well? What if quasar echoes contain evidence of time behaving differently on cosmic scales? There is growing speculation that space-time itself might have an underlying quantum structure, where the flow of time is not continuous but instead flickers in tiny, discrete increments. If this is true, then light traveling across billions of years could accumulate small quantum fluctuations in time itself, causing unexpected shifts in the arrival times of lensed quasar echoes. These fluctuations could be the first signs that time is not as smooth as it appears, that it is instead made of something more fundamental, something yet to be discovered. This idea aligns with a controversial but intriguing concept in modern physics. Time may not be a fundamental property of the universe, but an emergent one. In this view, time is not a rigid backdrop against which events unfold, but rather a consequence of deeper quantum interactions at the smallest scales. If this is true, then quasar echoes might be doing more than just reflecting light. They might be reflecting the hidden quantum nature of time itself. But here's where things get even weirder. If quasar echoes are revealing unexpected distortions in time, then it might mean that some of the signals we are seeing are not just echoes of the past, but shadows of the future. Could certain lensed images be showing us events that haven't technically happened yet, due to time loops buried within space-time? Could quasar echoes be offering the first evidence that, on a cosmic scale, the universe does not always play by the rules of classical cause and effect? This is not just a philosophical question. If even a small fraction of quasar echoes show unexplained shifts that cannot be accounted for by gravitational lensing alone, then we might have stumbled upon one of the greatest discoveries in the history of physics. Direct evidence that time itself is a more flexible, malleable phenomenon than we ever imagined. And if that's true, then lensed quasar echoes are not just a window into the distant universe. They are a window into the fundamental nature of reality itself, a reality where space and time may not be fixed, but instead, constantly reshaping themselves in ways that challenge everything we think we know. So what else is hiding in these cosmic reflections? What other secrets might be encoded within the flickering echoes of quasars, waiting to be unlocked? Could these echoes hold the key to unlocking the ultimate theory of everything, a theory that unites gravity, quantum mechanics, and time into one grand framework? One thing is certain: the more we study lensed quasar echoes, the more we realize that they are not just the curiosity of astrophysics. They are a cosmic mystery that could redefine our place in the universe. And if that's true, then the real question is, what will we discover next? The mysteries of lensed quasar echoes go beyond just bending light. They may be bending our very understanding of causality itself. If time delays between quasar echoes don't perfectly match what we expect from general relativity, it suggests that something more fundamental is happening. Could the echoes we observe be influenced by subtle shifts in the structure of space-time that we haven't yet accounted for? One radical idea gaining traction is that quasar echoes could be interacting with quantum fluctuations of space-time. In the realm of quantum physics, Empty space is not truly empty. It is a chaotic sea of virtual particles popping in and out of existence, fluctuating in ways that should be too small to notice. But what if, over billions of light years, these fluctuations accumulate, subtly altering the way light propagates through space? If this is happening, then lensed quasar echoes might not just be revealing distortions and time delays. They might be revealing the first large-scale evidence of quantum space-time foam. This is a concept where space-time is not a perfectly smooth fabric but is instead a frothy, ever-changing structure at the smallest scales. Think about it this way. If light from a quasar is traveling for billions of years through the universe, passing through the gravitational lens of a galaxy, and then reaching us, any small quantum fluctuations in spacetime could slightly alter its path. Over such extreme distances, even tiny effects could build up into measurable deviations, which could explain why some quasar echoes arrive at unexpected times. But if this is the case, it raises another mind-bending question. Could these echoes be revealing the hidden quantum structure of gravity itself? For decades, physicists have been searching for a way to unify general relativity and quantum mechanics. General relativity tells us that gravity is the bending of spacetime caused by mass and energy. Quantum mechanics tells us that the universe is made up of discrete, fundamental units. The problem is, these two theories don't fit together. But if lensed quasar echoes are showing unexpected time distortions, then they might be offering a clue. Perhaps the very fabric of spacetime is not smooth, but quantized at a level we've never been able to detect before. Could quasar echoes be the first astrophysical evidence of a quantized gravity field? Could they be the first proof that spacetime itself is made up of discrete, fundamental building blocks? Some physicists have proposed that if spacetime is quantized, then gravitational lensing itself should carry a hidden quantum fingerprint. The echoes we see from quasars might not just be affected by the visible mass of a galaxy, but also by subtle quantum gravitational effects that shift light paths in ways that classical physics can't predict. If this is true, then quasar echoes could serve as a natural laboratory for testing quantum gravity on cosmic scales. But here's where things get even weirder. If quasar echoes are revealing quantum distortions in time, then it might mean that the past and the future are more connected than we ever realized. Some physicists argue that time may not be strictly linear. That is, the past does not simply determine the future, but rather, there could be subtle feedback loops between them. This would mean that some quasar echoes might not just be showing us light that traveled from billions of years ago. They could be showing us light that has been influenced by interactions from the future. This idea, known as the retrocausality hypothesis, suggests that under certain extreme conditions, such as gravitational lensing across vast cosmic distances, quantum effects could allow for information to subtly flow backward in time. Could this mean that some quasar echoes are carrying signals that have been altered by events that haven't technically happened yet? If this is the case, then lensed quasar echoes might be the first astrophysical proof that the future can influence the past, at least on a quantum level. This could have enormous implications, not just for physics, but for our entire understanding of reality. For example, if the universe allows for small-scale retrocausality, it might mean that time is not as rigid as we think. It might mean that, under certain conditions, the future and the past exist in a kind of quantum superposition, influencing each other in ways we don't yet fully understand. And if that's true, then what does it mean for our place in the universe? Could lensed quasar echoes be revealing a deeper hidden order to reality? One where time is not a one-way street, but rather, a complex web of interactions across the past, present, and future? One thing is clear. We have only just begun to scratch the surface of what lensed quasar echoes might be telling us. Each new observation, each unexpected time delay, each unexplained anomaly could be a clue, a small but crucial piece of a much larger puzzle that could change our understanding of space, time, and the fundamental nature of the universe. So what's next? What will we discover when we start analyzing quasar echoes with even more advanced technology? Will future telescopes, capable of detecting even fainter signals and finer time delays, finally confirm that space-time is not what we thought it was? Or will they reveal something even more unexpected, something so strange that it forces us to rethink not just gravity, not just quantum mechanics, but the very nature of existence itself? One thing is certain: the echoes of quasars are speaking to us across the vastness of space and time. The question is, are we ready to listen? Lens quasar echoes might be the closest thing we have to a cosmic time machine, offering us glimpses into both the distant past and possibly even deeper, hidden structures of reality. If the anomalies in quasar echoes turn out to be more than just observational noise, if they truly hint at something beyond our current understanding of physics, then we might be standing on the edge of a discovery that reshapes everything we know about the universe. But let's take a step back. Before we dive further into the mind-bending possibilities, let's clarify one thing: why are these echoes so important in the first place? Gravitational lensing is already one of the most remarkable confirmations of Einstein's general relativity. When light from a quasar, an incredibly bright, distant object powered by a supermassive black hole, passes through a massive galaxy on its way to Earth, the galaxy's gravity bends the light, splitting it into multiple images. These images can reach us at slightly different times, creating what we call quasar echoes. Now, if general relativity is correct, we should be able to predict exactly how long it takes for each lensed image of the quasar to reach us. The light follows different paths, but all the paths are governed by the same mathematical rules of space-time curvature. So in theory, if we know the mass and shape of the lensing galaxy, we can calculate the time delays between the echoes with extreme precision. And that's where the mystery begins. Because when we actually measure these time delays, something doesn't add up. Some echoes arrive slightly earlier or later than expected, by margins that should be impossible under classical physics. These discrepancies are small, but they are consistent across multiple lens quasars. And in science, when you see repeated anomalies, you start to wonder, what are we missing? One possibility is that we've underestimated the complexity of the lensing galaxies. Maybe these galaxies contain hidden dark matter structures that subtly distort the paths of quasar light in ways we haven't accounted for. If true, this could be a new way to study the mysterious nature of dark matter, which makes up most of the universe's mass but remains invisible to us. But here's the catch: even if we adjust for potential dark matter distributions, some lensed quasar echoes still don't fit our models. That suggests something even deeper is happening, something that might force us to rethink our fundamental assumptions about space-time itself. One radical theory suggests that the deviations in quasar echoes could be the first direct evidence of extra dimensions. String theory, for example, predicts that the universe has more than just the 4 dimensions we experience, 3 of space, 1 of time. It suggests there could be hidden, compact dimensions that subtly influence how gravity works. If these extra dimensions exist, they could cause tiny, unpredictable fluctuations in the way light travels across the cosmos. These fluctuations might be too small to detect in our solar system, but over billions of light years, they could add up, revealing themselves as unexpected variations in quasar echo delays. In other words, every time we observe a lens quasar and find an anomaly in its echo timing, we might be seeing the fingerprints of hidden dimensions at work. But let's go even further. What if these echoes aren't just revealing extra dimensions, but something even more profound? Some physicists have speculated that space-time itself might be emergent rather than fundamental. This means that space and time might not be the basic building blocks of reality. Instead, they could be higher-level phenomena that emerge from a deeper, more fundamental structure. If this is true, then lensed quasar echoes might be the first observable proof that space-time is not a fixed, continuous fabric, but rather a fluid-like, evolving construct that behaves differently on cosmic scales than it does in our everyday experience. This could explain why some quasar echoes don't arrive exactly when we expect them to. Instead of light traveling through a static, pre-existing space-time, it might be navigating a shifting, dynamic medium, one where the rules of space and time subtly fluctuate at extreme distances. And if that's the case, then we are no longer just talking about understanding quasars or gravitational lensing. We are talking about understanding the very nature of reality itself. If space-time is emergent, then what is it emerging from? Some theories suggest that space and time might be a byproduct of deeper quantum processes, possibly linked to entanglement, information theory, or even holographic principles. Imagine this: What if the entire universe is fundamentally a vast, interconnected web of quantum information, and what we perceive as space and time are just our way of interpreting how that information interacts? Lensed quasar echoes could be giving us a direct observational test of this idea. If these echoes reveal subtle shifts that can't be explained by normal physics, they might be the first clues that space and time are not absolute, but rather emergent from a deeper, hidden layer of reality. This would be a cosmic revolution, one that could reshape not just astrophysics, but our entire framework for understanding the universe. And here's the wildest part: we might already have the data we need to confirm or refute these ideas. Over the past few decades, astronomers have collected observations of dozens of lensed quasars, each offering unique echoes across space and time. As our computational models improve, we are now able to compare these observations against theoretical predictions with greater precision than ever before. The coming years could be crucial. With new space telescopes like the James Webb Space Telescope and next-generation observatories on Earth, we will soon be able to measure quasar echoes with unprecedented accuracy. If the anomalies persist, if time delays continue to defy our best models, then we might be standing on the edge of one of the greatest discoveries in modern physics. Are quasar echoes just a quirk of complex gravitational lensing? Or are they a gateway to a deeper truth about the universe, one that challenges our fundamental notions of space, time, and reality? If we can unlock their secrets, we might not just be learning about distant quasars. We might be glimpsing the hidden architecture of the cosmos itself. And the echoes are still out there, waiting. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.